Pat Bartlett is a geologist, come mining engineer, dual qualified. He's been 57 years in the diamond industry, having started work with De Beers in 1965. I presume as a field assistant or field officer before he graduated. He has qualifications from Rhodes University in geology, a MSc from London University, and a PhD in mining engineering from the University of Pretoria. He has various other non-technical qualifications that are listed in the abstract volume from other institutions. He's worked for De Beers on the West Coast mines, Chuaning in the early days of the evaluation, on the various Kimberley mines, and he spent a large part of his career at Cullinan Mine, close to Pretoria. He's been a board member for Rockwell Diamonds, Petra Diamonds, and is currently an external consultant doing work on project development with a number of major mining companies. Pat is going to talk to us today about diamond mining methods applied to kimberlites and lamproites. Pat, over to you.
An overview of the contents and what I'm talking about. So first of all, have a look at a typical kimberlite pipe, because the mining method that is used on the mines is really determined by the shape and size of the ore body, and also by the dollar per ton of the ore in the ground. So most kimberlite pipes are pretty much carrot-shaped volcanic pipes, and the logic of mining the pipes is therefore pretty similar. And the second major item that I'm looking at is typical kimberlite and lamproite mine, the technical and financial evaluation, the steps that you would go through. And then looking at major diamond pipes worldwide, looking in South Africa, and really because I've got the best information there, looking at some depleted mines, Bultfontein as an example, looking at a mature mine which has been going for a long time, Cullinan, and then looking at Venetia, which is currently, well, it's almost ready to start producing from underground. So they're transitioning from the open pit to underground, and in a major mine that's planning to go underground, Chuaning. Then I look at some of the Russian operations and then other diamond pipes throughout the world, the main ones, and then some observations that are just making and some risks. I think it's important just to emphasize again that I'm just talking about kimberlite pipes. I'm not talking about the alluvial deposits or anything like that, because they add another dimension to it. But this is obviously just a model of a kimberlite pipe. So it's a carrot-shaped ore body going down. I think most of you have seen some version of this or the other. And as far as the mining method goes, right at the top of the pipe, you normally have, in the old days, it was a glory hole. I'll show you what I mean by a glory hole. And these days, almost all the major mines will start as an open pit. So near surface, kimberlite to a depth of 70 meters, sometimes a lot more than that, can be in clay-rich, soft yellow ground that historically was mined with a pick and shovel. These days, if you find something like that, you can mine it with a big loader. As they went deeper, they started to run into various problems. And in the old days, they used a mining method called chambering, which is very much like block caving in principle, but they didn't have the technology and it wasn't a very safe method. And so as the kimberlite ore becomes more competent below the zone of surface weathering, drill and blast methods are used, or in Russia, in some of those very valuable mines, they actually use road headers. So Mir International and ACOL all use road headers for mining. And as you get deeper and the shape of the ore body becomes complex, the size decreases, and that can constrain you from using various caving methods. And it might not be practical to use block caving. You might have to move to sublevel caving or some other version of underground mining. And some kimberlites are simply too small to allow block caving, and sublevel mining methods such as sublevel retreat are used below some of the open pits. That's typical on some of the Canadian mines. just a brief look at what I'm talking about. You mine the pipes, typical kimberlite and lamproite mine, technical and the financial evaluation. Starts off with a glory hole, and these days a benched open pit. The edges of the open pits are usually mined using blast hole open stoping, and below that you can use block caving or sublevel caving. And then also just a brief look at how the mines are financed, what the money side of it looks like. But typically, you've got an open pit, initially very little mining of the surrounding rock. Then you've got dumps in the existing pit. And with time, the pit goes deeper, and you need to put in the underground infrastructure that you're going to need to mine underground. And that typically will be a block cave, or it will be a sub-level cave. And this is switched around in some mines. Finch, for example, went underground using those blast hole open stoping around the edges of the pit up here. And when they went underground, they used block caving, block 4, and below that, Petra's been using sub-level caving. And what I mean by a glory hole is simply when this is Wesselton mine in the Kimberley area. It was found in 1895. And when they first started mining, they simply went into the hole and took the ground out. They didn't take any of the surrounding area. It was only what was in there. What you're looking at here is the geology. So at the top, you've got Karoo sediments, and this is the start of the Ventersdorp lavas sitting down there. Typically, your mine will start as an open pit, and this is just, I've called it NPV, but you can debate that. It's really the area underneath that line is the amount of money, the value that you have in your ore body that is accessed by the open pits. And then as you go underground, what's below the line is the value that you will have in the ground that's available to you. And this is the capital expenditure that you're going to need to spend to get that money out of the ground. So you start off generally putting a whole lot of infrastructure in, so that's quite high cost. And with time that comes down. But as you get to the end of the life of that pit, you start having to spend sometimes major money in creating the underground, and that creates a lot of problems. It very often means that the decision to go underground is delayed as long as possible. And eventually that dies away, or you might decide that you go even deeper, and then you have more capital expenditure there. And all the time you're going to have operating costs. So operating costs in the open pits are quite low, and they're often not that much higher, depending on the mining method that you use underground. If you use block caving, actual cost per ton isn't very different from the open pit. If you use sub-level caving, it's a bit more expensive. And some of the other mining methods are pretty expensive, like those roadheaders, cost you about $300 a ton to mine. This is just a look at Finch mine. Looking at from the top, you can see something of the surround. So they went, I think the bottom of the pit was about 340 meters. And they put in a whole lot of infrastructure to mine the remnants that were left by the pit. They couldn't get all of it out there. And then sitting underneath that, they had a block cave. And what I meant by your open stoping, blast hole open stoping, is on the left here, you have a diagram showing this is where I've got the cursor is the edge of the pipe. So as you get to the bottom of the pipe, you have quite a lot of ore left behind by the mining method, and you obviously want to get that if you possibly can. And most mines these days make a point of getting that. It's a quick way of getting ore, and it's relatively cheap. So these are the rings that people put in there, and by drilling and blasting, they break that ground up, and it's broken here. And then they use what is pretty much like sub-level caving to come in and collect that ore. In a couple of the mines, Finch was one of them, they used remote control loaders to actually get right into that open pit to collect what they could. So that's the first phase. As they transition from the open pit to the underground, they pick up what they can on the side, and by drilling and blasting, they take as much as they can of the remnants against the sidewall there. And when they go underground, certainly the Kimberley mines use block caving. So around the 1950s, they moved away from chambering to block caving using scrapers. If you went across to the United States, had a look what they were doing in the iron ore mines there, and adopted that method, brought it back to South Africa, and that was implemented fairly quickly on all the kimberlite mines in the Kimberley area. So all that happens here is you put a drill and blast, and you create a void that causes the ground above it to cave, and this can be 100, 200 meters high. And then you start collecting that ground at the bottom here. And rather than using LHDs, it's all scraped. It goes into passes, and then there's a train system down here which takes it back to the shafts or the crushers or whatever. More and more of the mines, they don't use that scraper method anymore. There might be one or two that still, but not many. They use mechanized caving. So instead of having the scrapers, the principles are still the same. You come in on your undercut level by drilling and blasting. You break out a horizontal slice of ore. And if you break out a large enough area, the ore above it starts caving under its own weight. And that broken ore is then collected in the draw points below that using load, haul, and dump vehicles. And some mines don't have sublevel, don't have block caves. They go directly for sublevel caving. There you can see an open pit, and underneath that you've got the infrastructure for sublevel caving. So there'll be, generally it's 4 levels that you're looking at. Or top level, you'll be doing mucking. That's where you've got broken ore. You're taking that to the pass system, taking it down through the crushers to the stockpile on surface and through the process plant. You often have another level below that where you're busy with charging and blasting, again, just creating ground to take out. Below that, again, you're charging, so you're developing that level. And underneath that, you're starting a new level. So very typically, you'll have 4 levels in production. This mining method works well for, depending a little bit on the quality of your ore, the competence of the ore. It's a bit more expensive. In Finch, it's about 50% more than the cost of block caving. So that's obviously a consideration. This is just an overview of major diamond pipes worldwide. And this is a very arbitrary definition. I've seen a major diamond mine is defined as a diamond pipe mine that has or is likely to produce about $2 billion worth of diamonds or more at current prices over its life of mine. And some of them obviously produce considerably more than that. And what I found quite interesting when I started looking at this, in terms of that definition, and I used that definition because I thought those mines are mines that have been around for a very long time. They've had a major impact, certainly on the regions in which they exist, and very often they've had a major impact on the countries in which they were found. And as I go along, you'll see what I mean. So in terms of this definition, less than 30 major mines worldwide. This is a table. I'm not going to go through all of it. It's just to illustrate some things. So these, what you see here, these red mines, this is the year in which they were discovered, and these were the Kimberley mines. So it's Bultfontein, De Toyspan, Jagersfontein isn't in Kimberley. It was actually on the way. When people were coming to Kimberley, there was Jagersfontein. We also have the De Beers mine, the Kimberley mine, Wesselton mine. So those mines, they started finding them in 1869. By 1891, they'd found almost all of them. Wesselton was the last one there. Other mines have been found as well. Frank Smith, a small mine. And these are far more recent mines, the Oaks, which was operated by De Beers, you have Fruespoort and you have Maasfontein. And if you look on this, almost all of those mines are now depleted. And if you look at Bultfontein, it started as a glory hole and then it went underground. If you look at currently producing mines in terms of that definition, sorry, if I go back to this column here, this is just my estimate of what the value in dollars that was produced by the mine over its lifetime. So if you look at a mine like Bultfontein, it produced for 110 years. There was some downtime there, but it was effectively in operation for 110 years, and it produced $1.8 billion worth of diamonds. If you look at the Kimberley mine, it was in production for 44 years. It produced about $2.9 billion worth of diamonds. And the values and the grades of these things are pretty different. It's very difficult to come up with an average over the life of these mines. So I think my estimates are probably underestimates, but those mines that you see there that now all depleted, they produced about $17 billion worth of diamonds during their lifetime, and obviously depleted. If you look at the current, in terms of my definition, major mines, you have 4 mines in South Africa now. You have Cullinan, Finch, Venetia, and Koffiefontein. Cullinan was also found 1899, Koffiefontein in 1870. And Cullinan has produced about $19 billion worth of diamonds in its lifetime. Finch with a lot. So that Cullinan went for 105 years, started as a glory hole, went underground. Finch has produced about $18 billion worth of diamonds in production for about 58 years, an open pit and then underground. Venetia, about $12 billion, going for about 30 years, still quite a lot to produce. And Koffiefontein, found in 1870, started as a glory hole, went to abandoned for quite a long time, or put on care and maintenance, then as a benched open pit, and now underground. And they produced about $3 billion worth of diamonds. So the value of diamonds coming out of those currently producing mines is about $42 billion. And in total, looking at what the depleted mines, as well as the current mining operations, have produced in total about $59 billion worth of diamonds, which is a considerable amount, especially considering that a lot of this was produced in the early days of South Africa. So it went a long way to funding the infrastructure, the rails, and everything else. It went a long way to financing a lot of the gold mines in South Africa. So these mines have certainly had a major impact and continue to have a big impact on the regions in which they exist. This is just an illustration of how diamond prices vary. So this is just, diamond is a very volatile commodity, and the variability in diamond prices is high. So this is just taken from a Petromine's recent trading report. So Cullinan, if you look at the most recent tender, so that that's tender for the end of financial year 2022, the dollar per carat value of diamonds there is $180 a carat. For the period before that, the half year before that, it was $192, and for the year it's $188. That's not much of a variability, but if you look at Finch, their tender force at the end of the year tender, 151, the previous one went to 97. So that's a huge increase for Finch. Koffiefontein, even more dramatic. Their tender 4, most recent tender, $856 a carat. And it was, for the previous quarter, it was $538. Williamson, the same sort of thing. I don't actually know what happened here, but if you look at the most recent offering, it's $369 a carat. And for the last half year before that, it was $760 a carat. So coming up with a figure for what the value of diamonds is problematic. And that's why I say I could well have underestimated what I think these mines have produced during their lifetime. I'm just having a closer look at these depleted mines. And most of them have been depleted after 100 years or so of production. And the example that I had a look at, or that I am having a look at, is Bultfontein. So Bultfontein, this is just a diagram, obviously, of what was there. It was found in 1869, started mining as a glory hole. And then with depth, it went to chambering. And below that, in about 1950s, it went across to block caving. implemented that. It changed to sub-level caving, and then they used a mining method called sub-level crater retreat or vertical crater retreat, and then it went back to block caving. And in 2020, eventually it went to a sub-level cave, and in 2020 it closed down. So it had it's 150 years of mining, really, if you look at that thing. Quite amazing, really, that a mine can last for such a long time. This is just not a very good picture, but this is what the mine plan looked like of Bultfontein in 1883. All these tiny little squares, which aren't that clear, are claims in the pit. They're 31 feet by 31 feet. So people had individual claims. By this time, they'd already gone down a bit. So there was a lot of consolidation of the various claims into bigger companies. And this is a photograph. I don't know if it's Bultfontein, I doubt it, but it's a photograph of Kimberley near surface mining operations. So here you can see this is the pipe, and this is access to it, and these were all the claims going down there. It was a real rabbit's warren. And as many as 50,000 people were employed in the mines by 1880. Quite remarkable, a massive rush. And as they went deeper, they implemented these endless rope haulages. So each one of those, it's a winch, or whatever you want to call it, will have a rope on it, and the ore will get loaded into a skip of some sort, get taken there, dumped, and so it goes round and round. And in places, they even use these ropes to go down in the skips to work in the morning. And this is just a look today at what Bultfontein, and this is Bultfontein here on the left, looks like. That was about 12 hectares at surface, and this is Bultfontein on that side. And that's the tourist plan there. It's got some of the biggest barbel that I've ever seen. They caught barbel there that were about 8 or 9 feet long, massive. And this is the joint shaft that services both of those mines. Petra operated, well, De Beers operated it for a long time, Petra for a short time. And now I think all of those mines are shut after a very long history. This is coming back to Cullinan, used to be called Premier Mine. And it was, they started operations in 1902. And by 1912, when this photograph was taken, you had up to 15,000 people were working on the mine. It never had all the small claims. It was owned by one man, Thomas Cullinan. And the mine operated for 365 days of the year, 24 hours a day. And that went on for a long time. And this is what it looks like today. So you've got a big hole there. It's 450 meters across, 800 meters across in that dimension. And then this is just looking into the pit. You can see some of the old tunnels. And this is just a brief history. It was registered in 1902. De Beers gained controlling interest in 1917. It was closed from 1932 to 45 during the Depression and then the war. They started as an underground mine in 1947. De Beers got the rest of the shares in 1972. They used open stoping, block caving, and then as they went deeper, they changed from scraper caving down to block caving. And there was a big project that was initiated. The plan was to put in a massive cave that would produce at the rate of about 10 million tons a year, but that was, they actually spent a lot of money and they started doing it, but it was never finalized. And the mine was sold to Petra, and Petra came in and they implemented very successfully a block cave, and they've also put in an SLC there. So that's just some of the history of Cullinan. And if you have a look at it from a different perspective, that's your glory hole on that side. So that glory hole went down to a depth of 280 meters, underground from 1947-48. And they operated 8 block caves, 6 open stopes, 1 sub-level caving, and in total, there were more than 400 kilometers of tunnels underground. You can see some of that infrastructure. And these are just some famous Cullinan diamonds. The Centenary diamond was found in 1988. It was sold to a consortium fairly soon after it was found for 80 million. And this is a value that you see there, the most recent value that I could find, that it's now been valued at 100 million. It was, when it was cut, it was 206, it was over 600 carats as a rough diamond. The cut diamond was 273. It's the largest, third largest found at Cullinan, considered to be one of the most colorless and flawless diamonds. And it was cut by De Beers with a special cut computer designed. I think there were 103 or 104 faces. And then this is probably the most famous diamond that came out of Cullinan diamond. It was that. You're only really going to know the value of a diamond when somebody pays you for it. But people who've looked at it say that in terms of the market, it should be worth around $400 million. It was 3,106 carats. It's a typical type 2 diamond. It was found in the pit sidewall. So that was one of the reasons people knew from early on that Cullinan produced big diamonds. It was cut into 9 major stones, and 2 of those sit in the royal crown and scepter and crown, and the rest of them were given individually to members of the royal family. This is looking at another mine. It's Venetia. They're actively transitioning to underground, and this is just a view. So you've got the main pipe there, K1, K2, and K3. I think that's K3, and there are a couple of other kimberlite pipes there as well. That's what the open pit looks like these days. It's come to the end of its life, and they're busy going underground. I think production is scheduled to start from underground in a big way by October of this year. And so this is K1 that you see there. You don't see it very well, but around the corner you've got K2. This is just looking at the plan that they have to mine Venetia underground. So that's the open pit, obviously. These are all the shafts to access the underground. The intention is, because of the awkward shape of the ore body, they couldn't use block caving, and they've used sublevel caving. So this is just the planned cave going down under there, sublevel caving, a huge amount of development. And this is K2. It hasn't been finalized as to whether they'll use block caving or sublevel caving, so it's still work in progress. And I think some of the major advances that you have, you can take your whole mine, so you can design the mine, and once you've designed it and looked at how you're going to mine it and put everything else in there, you can use a numerical stress model of the mining layout. And that's been going now for a while, and they're certainly getting better and better. So use finite element, finite different software, really to look at the stresses. So this is a high stress area. So even though it might not occur immediately, you know that those areas, your tunnels are going to come under high stresses. So you can design accordingly, and you make sure that your shaft system is well away from that. And it's just a great design tool. The other thing that I think is quite recent is they can go underground and they can map the tunnels with LiDAR. And there you can see this is just a typical tunnel underground. And any movement of that tunnel, you can see what's happening. And it literally picks up a couple of millimeters of movement. So it gives you a lot of very early warning of what's going underground. Again, just an innovation that I think is making underground mining a lot better, a lot safer, more predictable than it used to be. This is just looking at the Russian pipes. There were, or historically, there were 3 main regions. So you've got Udakhny, one over there. So this is way up in the northern part of Russia. I think the Arctic Circle comes through about there. They have about 6 to 8 weeks of summer. For the rest of it, it's winter. There are no roads. You can't drive from any of those areas to Moscow. You can use the sea sometimes, and otherwise it's all helicopters and fixed-wing aircraft if you want to move around. You've got the Archangel region there as well. And so this is Udachni, number one. Got Eichel, which is another area, and you've got Mirny. So Mirny is a substantial town these days, probably 30,000 people stay there. And Eichel and Udachni, probably around 10,000 people. And there's a number of alluvial deposits associated with the various pipes, but I'm not going to talk about that. So again, just a table. I'll point out some of the things. I'm not going to go through the whole table. A lot of the mines were found. The Russians started looking for pipes seriously, for kimberlite pipes seriously after the Second World War. And in a relatively short time, they'd found the Udachni kimberlite cluster, they'd found Eichel, and they'd found the Mirny cluster. And because it was so high grade, the Mirny came into production very quickly. Found in 1955, by 1957, it was in production. The others took a bit longer before they got into production. It's difficult, you can get the grades, it's very difficult to find out what the dollar per carat is of those. What seems to be a general consensus is that South African diamonds at one stage anyway were worth about $100 a carat, and the Russian diamonds at that time anyway were worth about $60 a carat. And these pipes, all the pipes in red were found very quickly in these days. And since then, the Russians have found a number of pipes. Haven't really been able to look at the value of these pipes in the ground, but they've certainly had a major effect. Everybody that stays up there really depends. So the towns of Mirny, Eichel, and Udachni are there because of these mines. Again, they started as open pit. 4 of them are now underground. And you had effectively 12 mines, which I think are major mines. If you look at this is just some pictures of that. That's Eichel, open pit. They're going underground at quite small tonnages. It's only 500,000 tons a year. They've been in production for some time. And this is Udachni. It's certainly a major hole, one of the biggest in the world. The final pit depth is 640 meters. What amazed me is that these faces, most of them are 105 meters high. If you think of an open pit, say here in South Africa, 15 meters as high. There they go to 105 meters. I think the permafrost helps them quite a bit. But here you have the portals allowing them to go underground. So the intention here is to go underground and put in some form of caving in these two lobes that you have down there. Eichel came down with an inclined shaft, and they've used road headers because they're very high grade. So they've used road headers to take that out. The mining cost here, I would guess, probably getting on for $100 a ton. The mining cost here, well over $300 a ton. International is an amazing mine from my point of view. It starts off, it was funnel shaped close to surface, down to about 125 meters. The average grade was 800 carats per 100 tons, high quality stones. So a ton of ore in International is worth about $1,600 a ton. And when they completed that open pit, it took them 19 years to get underground. Every problem that you can think of. They've got the permafrost, obviously, then they had oil, they had gas, they had mining methods, they had all sorts of problems. But it's a mine, it's going, produces good diamonds, and about 500,000 tons a year. And this is just having a look at other kimberlite pipes worldwide. Obviously, Botswana is a major producer of diamonds, probably the biggest producer of diamonds from mining operations. You've got Arapa, which was found in 1967, got the 2 Letlhakane pipes fairly shortly after that. And these mines are all found by Gavin Lamont, together with Tim Gibson. And then fairly shortly after these mines were found, or these pipes were found and brought into production, they moved Gavin Lamont down to Lobatse. and they gave him really a shoestring operation. In no time at all, he picked up another mine, Jordan, massive mine. These are just looking at dollar per carat, about $60, but by the time they finished mining, $21 billion worth of diamonds, if not more. And really, an absolutely amazing mine is Jordan, because the value of the production from there, the open pit is scheduled to run for about 41 years. It probably come to an end in 2032, 34. And then it'll go underground for whatever, 20 years or so, maybe more. They've got good quality diamonds there. The dollar per carat is high, so 130 billion really dwarfs an awful lot of the other production worldwide. Angola, you've got Katoka. Again, it's a very nice operation. You've got Uraxi coming into production. This is small, really. It's only 0.22 of a billion, so it doesn't have a major effect on Zimbabwe. Canada, there are no really big mines, but they're clusters which have certainly been very valuable. And this is just taking the figures that I've been able to get hold of. And the production from Ikati, Diavik, Gachakuri, Snap Lake, Reynolds, and Victor, it's over $35 billion in a relatively short space of time, because those first mines, or the first pipes, found in 1980, coming into production in 1998. But a lot of them coming to the end of their life now. So unless they find something new, Canada is not going to be producing for that much longer. Australia, you've got Argyle, and it's about 12 hectares in size. It was found in 1979, came into production in 1985, and went underground in 2013. Also a massive grade, but low quality diamonds. The open pit had a grade of 680 carats per 680 carats per 100 tons, I think it was. But the dollar per carat was very low. But in total, they probably have produced maybe $6 billion worth of diamonds. And the open pit was in production for about 30 years. Underground was in production for not very long. And Argyle was a problematic mine for Rio Tinto. I think the open pit went well, underground not so long. Maduri in Tanzania, massive ore body, massive pipe, 146 hectares, found in 1940. Went dollar per carat values are quite high. The last one that I saw was about $369 a carat, and they've produced in excess of $6 billion worth of diamonds, and they've been in production for a long time. It was an open pit. It was closed, I think, and on care and maintenance. I think it's looking at starting again. That thing, I think, is well worthwhile mentioning. I don't know what the total production of that has been. But yeah, worldwide, you've got 17 mines. And that's why I come back to saying that if you look at all the mines in the world, the really big mines, there's 30 kimberlite pipes that have been producing for a long time, had a major effect on the areas, regions, and countries often in which they operated. These are just some photographs of the various pipes. This is a Rapa. You can see they've got two lobes as you go down, and you can see that now in the open pit. And this is the Ikati mine in Canada, open pit followed by underground mining operations. At Gachakuri, it's owned 51%, I think, by De Beers, 49% by Mountain Province, operated by Mountain Province. This is Katoka, very nice mine in Angola. It's operated by Alrosa and Diamant, are the two big shareholders. This is Argyle. As I said earlier on, as an open pit, it worked well. It was a good mining operation. It produced some of these beautiful diamonds, the pinks and even a few blues, but underground was very problematic. The open pit produced on average about 9 million tons a year. When they went underground, the intention was to keep production at that same level, 9 million tons a year. They never got it much above 6.5 million tons from underground. And the original estimate of what it would cost them to bring the underground into production was just over $400 million US. They eventually spent over 2 billion. I think the final cost was about 2.2 billion on the underground mine, and it never, I doubt whether they got their money back. And this is what it looked like. So they had the open pit up there. They came underneath that with a block cave. And then on paper, they had sub-level caving. So there's considerable ore still in the ground, but I don't think anybody will have the risk appetite to go down there and do it. It was very difficult mining conditions. And this is, as I said earlier on, probably the biggest diamond pipe that's ever been found, most valuable certainly. And this is Jwaneng mine planning to go underground, just looking at some of the costs and what they intend to do. So what you have after cut 9, or maybe even a bit deeper than that, they've got 3 pipes. They've got the center pipe, south pipe, and the north pipe. So in total, you'll have 149 million tons of ore. The average grade 127 million carats, with an average grade of 85 carats per 100 tons. The depth of mining will go down to about 1,000 meters. And this is just some of the costs associated with that. So the tonnage that they have available from the 3 pipes underground is about 130 million tons. The waste, will have to mine some waste. They intend to recover 105 million carats. The mine grade, depends on what you do, 90 carats per 100 tons. The average diamond price, $175 a carat. So your average revenue per ton treated, $170 per ton is the revenue that you get, and turn that into Pula, close to 1,700. And the total revenue, this is in Botswana Pula, will be about 200 billion Pula. The costs, and this is with going underground, obviously, the operating cost is about 36 billion to mine that. The operating cost per ton is about $300 a ton. The capital associated with that, 36 billion, and your stay in business capital about 5 billion. And again, just looking at what happens in practice, you've got the open pit, which was in production for about 50 years, area underneath that line. And then you've got for the open pit, and then what the value of the ore that you have underneath the line here. So the value in that open pit was 107 billion, more or less. The underground is worth about 19 billion. As I said earlier on, this is capex. This is what it cost you. To go underground, the capital expenditure will be around 3.6 billion US dollars. And your operating cost will be about $4.1 billion. So those are just some very, probably order of a magnitude, not exact figures, but order of magnitude, which I hope are pretty close to what Jwaneng is worth and what it's going to cost to go underground. A lot of money. And these are just some of my own observations and some of the risks that I see coming along. Kimberlite pipes have been relatively easy to find once the target area has been defined. So in the Kimberley area between 1869 and 1891, they found a lot of the mines. They found Bultfontein, De Tooispruit, Kimberley, De Beers, Wesselton, and some mines that were further out, like Koffiefontein and Jagersfontein. In Yakutia, once they were in the target area, up there in Yakutia, between 1955 and 1958, they found a lot of the major mines and kimberlite provinces, Morne, Udachni, Aikon, in Botswana. In a relatively short time, once they found Rapa, Gavin Lamont, and Jim Gibson, Manfred Marks. They found the other 55, I think it was, pipes in that province. They found them relatively quickly. Dr. Lamont moved down to Lobatse, and again, in a very short space of time, they found Jonang, and I think there's 13 pipes in the Jonang cluster. In Canada, again, once they were in the right areas, once they knew what they were looking for and how to do it, it didn't take them too long to find Ikati and Diavec. They've been very efficient. The prospectors, and they're getting better. But all that I'm trying to get at here is you've probably got a fairly low probability of finding a new kimberlite province. People know where the kimberlite should be. And it's certainly not impossible to find another mine like Jonang. I certainly hope that they do find, but I think the probability of finding a new kimberlite province is probably not so good. And the other thing that I have here is going underground is an extensive and complex process involving technical, financial, and implementation risk. Both Jonang and Venetia have been continuously evaluating a transition from the open pit to underground for 20 years. And Jonang continues to do that quite sensibly. They've got to keep looking. You've got to evaluate the risk, evaluate the costs, what's in the ground. As I mentioned earlier on, Argyle going underground cost far more than planned, and it never achieved its planned production from underground. And I don't think it made Rio Tinto money from underground. International, the Russian operation, small one, took 19 years to transition from that open pit to the underground. Permafrost, gas, oil, you name it, they had the problems. And this is just a general look at some of the risks associated with implementing projects. And this is mining projects. This is work that was done when we were looking at taking Cullinan underground with the CCAT. So what this table says, starting right here at the bottom, how many projects come in on budget? And you can see the figure here, about say 53, 54 come in on budget. If you look at how many come in on time, about 45% come in on time. If you're looking at both time and budget, 25%. If you look at some that come in a bit better than what they predicted and come in, it's 15%. If you're looking at predictable, fast and low cost, less than 10%. They work as expected. In other words, in terms of what you expect them to produce, you're looking at maybe 7 or 8%. And then if you bring safety into it as well, very few mines. So it's a technical challenge for anybody to go underground. And I think mining people are very well aware of that, especially the people who have to supply the funds from the big mining companies. And this is just a little bit of an overview. If you do what you should do, come with the conceptual studies, the pre-feasibility and feasibility, and you do good planning, and you do good execution, you're probably going to have a good project. If you don't go through those phases, and these days very few mining projects seem to go through all those phases, you end up down on the low road down here. So you might have good execution or poor execution, but yeah, the poor project manager, he's under tremendous stress all the time. Probably doesn't last that long. They come and go quite rapidly. And I'm not going to go into this in any detail. It's just looking at some of the additional risks that you have. This is common to all mines. I think something that is becoming increasingly important is the license to operate. If you can't satisfy the country and the people, the chances of you getting to mine are pretty small. And that's it from me. Thank you.
But the Alrosa website has got a lot of very good information. I mean, you know, they do quite regular investor reports in PowerPoint format, and there's fantastic information in there. And they also publish annual sort of management reviews, going into quite a bit of detail on their operations, including grades and, surprisingly at times, diamond prices for the individual operations.
Thanks, Paul.
Worth a look.
Thanks, Bill. I'll have a look at that because I did struggle to really come up with something that I could say.
I was
exactly how
actually,
much those guys
I
are
was
putting in.
amazed at the amount of detail that was on there. And I'll send you a couple of I'll send you a couple of examples, but you know, you can troll that website for days, I tell you.
Oh, thank you. Thank you.
Yeah, but I mean, they effectively a public company, so to speak.
Yes.
It's a very good website. Yeah,
Yeah.
yeah, it's
Now,
been amazing.
Archangel Diamonds, for instance, is completely the opposite.
Yeah.
It's very difficult to find information.
Okay, there's a question in the chat box, Pat, if you can have a look, or we can read it to you about why some of the reasons mines would change their method.
Well, I think if you look at it, obviously you change from an open pit to underground because it's just becoming prohibitively expensive. Your stripping ratio becomes more and more, and you're moving a lot of tons to get a ton out of the open pit. So eventually it becomes cheaper to go underground. You've got to consider risk as well. And then when you go underground, I think most mines have chosen to go with block caving because block caving is not that expensive. It's technically quite difficult. You have to put a lot of your money up front. Obviously, you're spending maybe for 5-6 years ahead of getting any production out. And then as you go deeper, a lot of mines have transitioned to something like sub-level caving. And normally that is because your ore becomes more competent and the ore body is not big enough to allow caving. So it's really an assessment of the shape of the pipe and what you can get out of it that makes you change your mining method. There have been some others where I don't really know what the logic was behind vertical crater retreat. I think the only reason that I could ever find why Bultfontein went to vertical crater retreat was because they had a mine manager who came from Prisca, where they'd implemented vertical crater retreats on the copper mines there. And he thought it might work, so he implemented it. And also with the open stopes, the massive open stopes at Cullinan, it was, when I got there in 1983, all the mining guys said, well, they never thought that these open stopes would work, but the planning guys did, so they went ahead, they implemented it, but it didn't work, probably because people weren't that dedicated to making it work, and they just referred it back to block caving. So sometimes it's good technical reasons, and sometimes it's really just, I don't know, differential engineering or something.
Yeah, I think sometimes it's the boss. You get these big mining characters, Pat, who did it their way and impose their methods on. I mean, you can probably name some of them, and I presume that's why engineers are always behind schedule and over budget. Particularly in these big mining companies where you have so much redundancy built in, and they just keep spending money. Geologists can budget, I would think, Bill.
Yeah, but I think, to be fair to the mining engineers, if you're now stepping back, to the late 1940s and so on, reopening all these underground mines. No one in Southern Africa had done anything like that before, to the best of my knowledge. So, as Pat said, they were, going all over the world trying to find new methodologies and things that would work for them. So there's been a lot of learning, I think, in the last 60, 70 years. And, mining today, I think, is very different to what it is now. And it's the same in exploration and all these things that we're busy with. The way things are today is not the way they were at that time. And people had to make, they were making risk decisions based on, you have to believe the best information that they had at the time. And yes, at times it would have been, a bit of a bet on this and let's see what happens type of thing.
Well, I agree with you. I think that these days the mining engineers are very professional at what they do. And when when the unexpected happens, they've got to deal with the situation, and that's often the problem. It's just they didn't anticipate. Like Argyle, the one thing that happened to them was they knew that it was going to, that eventually they would cave through to the open pit. What they hadn't anticipated was that there was going to be massive rainfall. So they ended up with the pit flooding, and at that time they were in the process, or they were almost ready to cave through. So for 9 months they could do nothing. And things like that are very often what catches you. You just you can't anticipate everything. You can look at the risk, and you can do and they're good at it. I think a lot of the mining engineers are very professional.
I think, Pat, one of the big successes was the Premier project going under the sill, the caving of the sill, which was, I mean, people faced that with trepidation in the 1970s when they were looking at it, 60s and 70s.
Well, they did. And there was a lot of study on that done, but eventually it was the guys on the mine that said, well, we think we know what to do, and they just went ahead and they did it. And it worked pretty well. It kept the mine going for a long time. Obviously not perfectly, they learned a lot. But I think the going under the sill was successful. It's kept that mine going.
It's been an amazing mine, Pat. And just for interest, Jean Honey and his team at Akapa Mining are doing a great job on, I don't know what the correct word is, Andrea, maybe you can comment on, scavenging and mining around the old joint shaft. So there's actually, quite a lot of ore coming out of the joint shaft, surprisingly. And that ore gets, they also still mining or reprocessing the tailings. And John and his team are absolute masters at running rotary pans, which are, as extremely inexpensive to run. So Kimberley too is really ticking along, and if the prices that we're seeing sort of maintain themselves, other sort of older operations or small operations, I guess, will keep going for longer.
Yes, I think there's people are getting, certainly with the diamond price going where it is, you're going to get a lot of people coming back into the diamond business, mining alluvials and small mining operations. They will, and a lot of the old operations, people like you say, in Kimberley, they'll go back in, and they do. There's other mines like Camphor's Dam. People have looked at that time and time again and never actually gone to it, but it's a fairly substantial open pit.
I think the problem there, it's been overrun by the community, by the communities and informal housing.
It has. So.
Yeah. And Andrew just reminds us, Wesselton too is also still producing.
I'm glad to hear that. I'm glad that they do.
Thanks, Pat. That was a lovely overview, and really appreciate it. It just goes to show, and I guess, I had a question, just a road header. Maybe you just want to quickly explain before we end what a road header is. These big things that chomp up the roads when they're retarring them, that the Russians use so regularly.
Well, it's almost like that. They use it for developing tunnels. So the Lesotho Highlands water scheme was developed using a road header. It's really just a big cutting head that they go in and they cut the rock with it. And it just advances slowly, maybe 5 meters a day in a tunnel, and that material comes out and they take it out. It's an expensive way to mine, but if you, in a mine like International or Marne or Eichel, where the value of ore in the ground is huge, you can afford a mining cost per ton of $300-400 a ton. It still makes you good money.
Yeah, thanks, Pat.
Sorry, John. I must just quickly say that the machines we used in Lesotho were known as tunnel boring machines, not quite a road header. A road header is almost like a tractor a back actor with a long boom, and on the front there's this rotating head that cuts the rock.
Oh, you're right. You're right. The road headers that they used, They even used one for a while at Cullinan to put in the tunnel development, are a lot different to what they used on the Lesotho Highlands Water Project. It's the same sort of technology to an extent, though.
Correct.
We're now moving into the realms of crushing rock, breaking rock, and recovering diamonds, and most of all, making sure you don't break them. So thanks to Derek Leahy for having his team present to us this afternoon. We're going to have two presentations, initially by Derek and then two of his colleagues. Derek completed a national higher diploma in extraction metallurgy at the Technikon Witwatersrand School of Mines. He is a member of the South African Institute of Mining and Metallurgy and is the managing director of Consulmet Pty Limited. And he's going to talk to us today about two very interesting kimberlite mine projects which the company is currently involved in. So over to you, Derek.
Okay, thanks, John. Yeah, look, I think we're quite lucky. I was just listening to these road header continuous mining tool subjects. So we're quite lucky today. The last 2 years, we've had we've developed a hard rock kimberlite plant, a big one, 500 tons an hour, and then we've been been lucky to just after that do a very soft kimberlite. So I'm going to compare the two today, and some new bits of technology we're putting into the flow sheets, show you what we're doing, what's out there. And before I start, let me just go to my intro. I just thought, John, we're always talking to students as well. Amongst all the old dogs, we've also got a lot of students. So I thought I'd introduce one of my bugbears, which is good process engineering basics. All these big projects, I see a lot of things going wrong, as we all do. We're talking about mining, but also in process. And I wanted to go through some good process engineering fundamentals, like absolutely basic, which might seem very basic to a lot of us. But yeah, if we are talking to the students, I just want to get that out the way. Then I will go to the hard rock kimberlite project that we've done in Zimbabwe. And then I'll talk about the highly weathered tefacious type of kimberlite that we've been doing in Angola, that we're busy with right now as we speak. Both these projects are very recent. The first one's being commissioned as we speak. The second one's currently in construction, only with the bulk earthworks. So good recent history here, and nice for everybody to have a look at it. So I'll just move on to my little bugbear with some fundamentals. So flow sheets and PNIDs. I mean, all projects start with a flow sheet and then a PNID. But I see a lot of guys just doing really simple line diagrams for flow sheets and really not putting any effort into the flow sheets and the PNIDs. And actually, that's your vision of your plant. That's if you're a good senior process engineer or process manager, that relates to the layout, ultimately to your layout, your mechanical layout. And the more care and attention done to the flow sheets and the PNIDs, the better your plant deliverable is going to be. And we seem to be losing a lot of the darker arts of process engineering, well, all the basics, actually. It's not even dark arts, the basics. So, yeah. So I just wanted to highlight the importance of professional flow sheets. I mean, it's the senior process engineer. It's his vision. It's his vision through the flow sheets and PNIDs, and that translates to a good general arrangement. So what do we get out of it? Well, we get quality mechanical equipment lists. We get all your installed kilowatts critical to your OPEX. We get great mass balances. I see terrible mass balances out there everywhere I go, and it's basic stuff. Your solids balance and your water balances. And guys just get it wrong, and then they can't understand later on when all the equipment size is wrong and they're getting there's no safeties, etc. And detailed PNID information. Also a lot of basics which are forgotten. On these bigger projects, you can probably get it away with on small scale things, doing things pretty basic. Mid-tier, you can do the basics correctly, but on your large projects, you need to take a lot of care and attention and take time in your initial design phase, which will save you a lot of pain. So just for the students out there, I just put, this is a DMS flow sheet. I wanted to put just a couple of the red bubbles are the basics on the flow sheet. Battery limits. It's amazing how often, you know, the guys get the battery limits wrong, either within the company, between their own modules, between the DMS and the recovery, or between other contractors and subcontractors on big projects. Those battery limits are critical. All the little lines with the arrows on the ins and outs of the plant. Detailed mass balances, percent solids volume by volume, percent solids by mass, your water balances, and your solids throughput through the plant, and doing a fines, a middlings, and a coarse balance on your flow sheet, so that you understand the parameters of your PSD. Now, you've designed for a PSD, and not absolutely critical. I haven't put it here, but starting with a good PSD and having the window, a nominal PSD between your max and your max coarse and your max fines, having a nominal PSD, particle size distribution, absolutely essential. It's amazing how many projects go wrong when the PSD is wrong, and putting it on your mass balance so that everyone can see where it came from and understand it. And on the right hand side, the right hand bubble, we obviously have so detailed mechanical equipment lists and kilowatts. And I see the more detail you put on the flow sheet, on the mechanical equipment list on the right hand column, the equipment sizing, the installed kilowatts. It was a vibrating screen, put 6-pole motors, 8-pole motors, model numbers, just a lot of detail. It shows you put care and attention into it. And then the right hand side, obviously your kilowatts are critical. So just a little basic lesson. Get the guys out there are just doing simple line diagrams, and there's so much you can put on a flow sheet. Here's the vision of the plant and the creative side of the plant. And like I say, a good process engineer will translate that into a good general arrangement drawing, which benefits everyone in the long run. Next is onto P&IDs. All right, thank you. Okay, P&IDs, we can see here just a lot of detail in the average P&ID. The guys are doing so many things wrong on these P&IDs, which you can go into so much detail. Just have a look at the spray bars, your distance between your spray nozzles, your valves, your width of your spray nozzles across the screen, the valve details, lining details, pipe details, minimum slope on your pipes, P&ID control loops, and sump valley angles. A lot of guys take the P&IDs for granted, but good longevity on the project, on a big project, and a lot of detail into the P&IDs, absolutely essential. Good design fundamentals. That's what we do. Okay, so the first project I'm going to move on to is a 500 ton an hour hard rock kimberlite process plant, 90 MPa plus. It's in southern Zimbabwe. It's been around since 1998. I was quite lucky. I did the original sampling plant when I was still with Bateman's. I built the first sampling plant. It's been a very successful project. They're moving on to a bit of lower grade material now. There's 3 pipes. And as I say, the kimberlite's sitting at about 90 MPa. And so milling was out, autogenous milling was out. And we had to do conventional crushing. We've got 4 stages of crushing here, actually. I'll show you all the layouts just now. For us, it's quite a big project. Design, fabricate, transport, and install 325 superlinks. As I say, we're busy commissioning right now. 5,500 cubes of civils, 8 megawatts installed power, and just taking note, big circulating loads. We had massive circulating loads. A lot of granite dilution, which doesn't help and increases those circulating loads. I think in the future, waste sorting is going to be so. Where we're going with waste sorting, with the near infrared and all the optics and all of those good things, I think it's going to make a huge difference in these type of deposits. We in our infancy there, but it's going to make a difference. So, yeah, as we can see, southern Zimbabwe, right next to Moroa, or at Moroa. Right, off we go. Big plant, as you can see, big footprint, almost old style footprint. we've got a huge a dump of low-grade tailings, and bottom right-hand corner we've got the two front ends. So the left-hand one is tailings only. The right-hand one is run of mine from the pits. The two pits are very competent. Some of the low-grade material is very competent, and then their pipe 3 is highly weathered. So we had this dichotomy of ore to deal with, and I'll show you on the scrubbing what we had to do when we treat pipe 3. Yeah, so we've got double scrubbing. We've got a primary scrubber, then we've used these rotary log washers as a secondary scrubbing unit for the highly weathered material. We've got Kawasaki IMS secondary crushing. We've got VSI Techrock VSI for tertiary, which we call quaternary here, because we've got a pre-primary, because we had a very big lump size. So we put a pre-primary jaw and a primary. So we got clever with the labeling. But yeah, so we ended up with quaternary crushing. You'll see a lot of stockpiles, and I'll come to it later. And I think it's something, if you've got long duration, if you've got a 20-year life of mine, or even a 10-year life of mine, 20, 30, 40-year life of mine, you know, we go to these big plants, and some of it's weather conditions like Canada and Russia, and you can't put stockpiles due to the igloos and the limited space. But if we are out here in Africa and you've got the space and you've got 30-year life of mine, I don't know why people don't put stockpiles. You know, try save money on the civils and not put stockpiles. I understand people come with security and all sorts of things, but really from a plant availability and utilization point of view, makes a huge difference. I mean, in this plant here, you can isolate all your areas and run your XRT modules in the middle here, and run your DMS, and you can run your individual secondary and tertiary crushing circuits alone if you have any maintenance on the rest of the plant. So yeah, I'd say a forgotten art in some of the designs. Guys are going for really compact plants, which I understand in a lot of circumstances. But if you have a long life of mine and you want to push up your availability and utilization, let's not forget the good old stockpile. Yeah, the summary of this plant, it's jaw crushers up front, and then we've got a primary rotary barrel, just a big scrubber. We've got log washers as secondary scrubbers. Secondary crushing is the IMS Kawasaki crushers, which are the groove liners. I'll come to them just now. The groove liners, which have been quite good for diamond breakage with the interparticle crushing. Tertiary crushing, to save costs and power, instead of HPGR and that, we're using the VSIs with the rotors, with great success on many low-cost kimberlite operations. All the +10 here, all the +10 is off to 3 XRTs, and then we've got a very coarse distribution. So even with the XRTs or bulk X-ray, you end up with 3. We've still got 3 by 200 ton an hour DMSs because of the big circulating loads. And then for the DMS conchs, we've got a final X-ray sort house. We were using the new DebTech Mark IIs. I'll come to those now. They look like really great machines. Yeah, and so it's interesting. Both the designs I'm going to show you now, both of them are using XRT on either +6 on the second project, and in this case +10 or +8. So both designs, XRTs or bulk X-ray, has just become standard on as a coarse concentrator. Anything +6, +8, +10. I find them really great on kimberlite because you get a very low yield and direct to hand sorting in most cases, depending on the mineralogy. But in the cases I've dealt with in both these projects, very, very low yields, and you can go direct to hand sorting. So yeah, whereas again, 12 years ago when we started putting XRTs in as primary concentrators, and it's now become a standard piece of kit now. And the DMSs for fines, we still can't get the capacities and the recoveries. We're still using them for fines recoveries. And again, over a 50-year life of mine, the good old DMS is still doing its job in the circuit. We've got a big thickener. Well, not so big. The second project is quite big. This is a coarse kimberlite, so we don't really have a slimes problem. We have smegtite, which causes a bit of dispersion and some settling problems, but it's not a massive challenge. Our challenge here was the crushing efficiencies and crushing efficiencies and circulating loads. Yeah, so quite interesting. We've got two modules like you see on the slide here. One is for tailings only, and one is for fresh feed. This is the fresh feed one, and you can see we're using Osborne crushers. Osborne, what we call a pre-primary, because we've got a big lump size and we just nip it down. We've got our Osborne prime, what we call a primary. It's a secondary crusher, just to get it down to size to prepare it for the IMS Kawasaki's. Used Osborne here, no complaints, been fantastic. Funny enough, just talking about cost and money, on another project recently up in Lesotho, with the client, we made a decision to buy a Chinese crusher, a jaw crusher, which was still quite expensive, but about a fifth of the price of say an equivalent Osborne or Metso or any of the Sandviks. And they're just interesting. The crusher crushes beautifully, no problem. So the quality wasn't bad, but the forces we got, were crazy. So all the forces were out of balance, and the civil design and the civil rectification work we had to do on it. Actually, we should have just bought a crusher for 5 times the price, because it just ripped itself out of the civils and that. And I must admit, the new jaw crushers on the market today from all the big suppliers, really all the forces are balanced within the machine and make a big difference on your civils, even though you can see there's still significant civils here. Yeah, so we tip, we've got an apron feeder, we've got a VGF, pre-primary and a primary. That's just the front end, nothing special. The nice thing is that right on the back, this corner here, where we're feeding the tailings, we can also feed fresh feed. So you've got redundancy in the feed. I always believe in bottlenecking the plant downstream and really overfeeding if we can, the front end. So really bottleneck downstream. And we've got quite a bit of over design in the 2 front ends to just ensure that we bottleneck the DMSs and the XRTs. So primary and secondary scrubbing. Primary scrubbing, we just went to a big washing barrel. Secondary, we've been trying these units out from Ireland. This is the 4th project we're putting them in. We put 2 big ones in here, the CDE 250s, and we're very happy with them. I think over the long term, it's going to be interesting. We've put them on smaller kimberlites and on alluvials with great success. Really clean, sticky material up nicely as a secondary wash. I wouldn't put it as a primary, because it can't handle the lump size and the aggression of a high lump size. But as a secondary, to really clean it up as preparation, and especially in consideration of bulk X-rays. Your feed preparation and any X-ray, whether you're putting a Bureveshnik or a Tomra XRT or whatever on a bulk XRT or X-ray, your feed prep is becoming more and more critical. And we've installed 2 of these now. One of the unintended benefits, which I've discussed for John before on the alluvials, is the elutriation. And we get an elutriation with all the organics, blasting caps and vegetation. Any vegetation in the dump material, we actually can float off the back here and elutriate and then dump it in a bag on the back. But it doesn't then, if you're using XRT, which ejects the carbon, you don't have that as big a problem. You still get a problem, because interesting, a lot of the wood is fossilized, so it's still heavy. So you don't get rid of all your wood chips and everything. But some stuff does go through, and but you clean up 60–70% of it. So yeah, not great clay, because mechanical attritioning, so it gets rid of clay, and a benefit out of this, of course, XRT has been elutriation, which has been a bonus. In all of these things. Again, these are 2 big projects. This particular project with coarse kimberlite with a lot of silica and granite. I'm going to be very interested to see long-term the tungsten paddles, these tungsten tip paddles, how they're going to last. I love this arrangement. This non-helical spiral arrangement is brilliant, pushes all the material beautifully and smoothly out. We've tried other units with the old paddle log washers, and we've tried different arrangements, and they haven't worked so well. So this non-helical spiral arrangement is fantastic. And as I say, the big test now is going to be how many hours on large tonnages are these tungsten tips going to last. So far, the last couple of years, we're doing quite well on smaller mines, on into the really, really well in some of the data we're getting back. But yeah, that's going to be a test, and we're going to check it out. Okay, let me just move on. All right, next to this, you can just see our secondary modules here. There's the log washers, log washer product. We go to classification, and then plus 25 all comes back into these secondary crushers, which I think they IMS 1300, Kawasaki 1300, so they're big units. We again probably on our 4th project with them, and very happy with them. I mean, some guys have had problems with them. I was speaking to some guys from DRA on one of the big projects, had some massive problems on the IMS units, but so far we've been quite fortunate. I think it's also probably the way you install it, maintenance, regular maintenance, the way you operate it, but you've got to look after them. It's got the grooved liners, as I mentioned. John did mention diamond breakage earlier. I don't think I'm going to get too much time to go into it. But we with the interparticle crushing, we have seen a slight benefit with the groove liners in these units. I mean, they're using them up at Letseng. They put them in at Likabong. I saw them at Likabong, and I've seen them. Yeah, so they are benefits, and we're quite happy with these units. Okay, I'll just move on here. So we always got that old dilemma on recrush, getting at cheaper capital units, not wanting to spend money on a high pressure grinding roll. The hardness of the material, if you've got really hard kimberlites with a HPGR and the maintenance on it. And yeah, over the years we started with the VSIs, and we sort of followed the chief engineer. I think I was talking to John yesterday. It's funny how you follow people, but right back to the old Barmek days, with the Sodala, Barmek Sodala license. And then the chief engineer moved on. I don't know where he went. And then he moved on to Osborne, and we put Osborne units in. And now he's moved on to a company called TechRock. And we're really getting the drop boxes right, or the flood boxes and the dead boxes right, and getting the pedals, because they're high maintenance on the pedals, but getting those pedals right. Diamond breakage, yeah, I would say not obviously not as good as an HPGR, but probably fit for purpose. Remember, we're already down we into the finer diamonds here for fine diamond liberation, and so I suppose that exercise has still got to be run. But as a capital and on an efficiency point of view, on our percentage passing -6, we're getting wonderful results, and it's going through. But I'm sure there'll be a lot of arguments on diamond breakage, but I'll just be careful. This kimberlite's incredibly aggressive, and an HPGR will take a lot of pain as well. So yeah, that's our tertiary crushing units. You can see a big layout at Zimbabwe, quite lacquer. You've got the big granite copies in the background. Really nice site, Rundi River, 10 kilometers away. And as I mentioned earlier, we're busy commissioning, so that's quite nice. Competent material, we couldn't get away. Unfortunately, we 8 or 10 millimeter cut on the coarse side, so we went for our good old DMSs. Each DMS 4 times Multitech 420 millimeter cyclones, each 2 Multitech cyclones fed by a Y-shaped distributor. We put one of those Y-shaped distributors in 17 years ago. I think they're absolutely awesome in getting equal pressure and equal flow to your twin cyclone installations. And we're very happy with the DMSs. We've commissioned them, they're running well. And you can just see, if you go, all the concentrate, our security is not in place yet, but all of this is going to be red area. This was taken in February. This picture was taken back in February. You can see this will all be banked off, and we are jet pumping each of the fractions up to the central recovery plant with the X-rays. In the background, you can see the XRT feed conveyors. So there's a bank of 3 XRTs for the plus 10 millimeter, plus 8, whatever it is. There again, you can see the DMSs. Just one of my old bugbears. I think a lot of people know I've been around a long time in the DMS business, but the guys are just not, the DMSs are getting more compact. Guys are building them compact, but they're not taking into account their cyclone selections are inadequate. Medium to ore ratios. I've seen some DMSs in the market at 3.5, 3:1 medium to ore ratio. And everyone's saying, well, I've got where we put a 55 kilowatt or 75 kilowatt on a cyclone feed pump. There, guys are boasting that they've got a 30 kilowatt, you know, and so they're saving money. But their medium to ore ratio is 3.5 or 3:1. I don't know what that's doing to their diamond recoveries, but it can't be good, especially on fines. Plate work designs are terrible at the moment. Header boxes and sumps, you know, minimum plate work angles, pipe work angles because of heavy medium. And then maintenance, maintainability and operability. Again, on a bigger mine, you've got to take a slightly different mindset. And life of mine, maintenance and accessibility. I was going compact for everything, and then the fitter and the boilermaker can never work on a pump or get it out and work on it or get to it. And yeah, so you've got to think about maintainability and operability. It's a big factor. Basic designs, I know, I understand with the juniors, the mid-tier, not so much, but the juniors, I understand when the plant has to be compact and a rotary plan's got to be put in as is. That we understand that. And you've got a world-class deposit, and you must treat it with the respect it deserves, and make it easier for the guys running the plant. Okay, I just put we had a massive degrit because of that granitic kimberlite and all the contaminants. We've got a huge degrit circuit here. The photo doesn't do it justice, but it's about 15 meters in the air. Massive degrit. A lot of projects undersizing their degrit. You're trying to reduce as much grits to your thickener. I just wanted to a great thing that's happened in our business the last 7 or 8 years is preconditioners. You know, instead of coagulants, much cheaper preconditioners, and charging the water or changing the charge on the water, and just preconditioning the water to save you on flocculant and help you with clear overflow, clear water. We use this VAT slurry tech. They do a lot of our test work, this Clary V44. And it just charges up, all the overflow goes to the slimes dam and then comes back as return water. So it's not a continuous dosage. You maintain the level on conductivity. You have a conductivity meter and you have a pH meter. And you see the levels drop, you just add a bit more. I add it out at the dam or add it into the plant anywhere here. And what we, in previous applications where we haven't been able to get kimberlite slime settling at all, this has been a massive game changer where the slimes is actually settling. We're getting clear water, not so much more compaction and underflow density, but we are getting your shear forces for your pumping. Your viscosity is lessening a bit, and we able to. I mean, Yashin after me will talk about those big pumps at the CTP, and in the old days. It was just impossible to pump a high viscosity and the maintenance. So he'll chat about that. But yeah, we're able to reduce the kilowatts on the pumps and makes a big difference. So makes a lot of kimberlite slimes that we've looked at in the past were just impossible to treat. It's a bit of a game changer. Yeah, I brought this up earlier, but I'll bring it up again. Stockpiles, I've used stockpiles and this and on the next project as much as possible. You know, the more compact our plants are going, you've got a problem with a XRT or a small problem in the DMS and you end up shutting your whole plant down and have these arguments all the time in operations. But you've got to think about your overall availability and utilization. So the more surge you have, is good. You know, it can help you fix a 8-hour problem in front of this or whatever you have to do. We're building all our tunnels above ground, so we're not going underground. Got a really neat design now. The little blue rectangles there, you can see where the feeders are going in. and a lot of duality on the feeders. We only need 2, but we've put in 4 per tunnel. This is the DMS stockpile feed tunnels. Okay. Yeah, so I'm going to just race straight to the final recovery. We're trying the new DebTech machines, the new Mark IIs. They were expensive. Yeah, very expensive compared to the flow sorts, compared to the Bureveshniks. We chose 5 of them for this project. And yeah, the proof will be in the eating shortly. There's material going through them now, and we'll have all the data. But very impressed with them to date. I mean, the number of settings we can set them. There's about 20 or 30 variables you can play with, so you can really fine tune. I'm not an expert on it, but I'll get to know it over the next couple of months as we commission. But you can sort of fine tune your machine to your product and really set it up nicely. It's a wet machine, and we're quite happy with them. The compact layout of the machines has been good. Slightly higher capacity on fines than, say, the flow sort, and we spend more on capex, but it's interesting how the final recovery building compacted a bit. So more on capex on the machines, but the height of our final recovery building came down a bit from, I think we would have had to select 12 double pass flow sorts here, equivalent, which was still cheaper than these machines. But our building was another 8 meters higher. So the recovery became quite compact using these. And I haven't got data yet, but hopefully they made out to be. So far they're looking quite nice. As compared to the old Mark I's, I just gave advantages. I think the big thing, the Spellman X-ray system, you can see they put a Spellman X-ray system control cabinet as compared to the old one built into the machine. I like this advanced diagnostic capability. As I say, I'm still getting to terms with that, so nobody asked me anything too complicated. I think it's maybe not the right machine for out in the bush somewhere for a small show, but when you've got, again, a long life of mine, and you've got the technicians on hand, and you've got the capital, and you want to do it properly, and then you can make use of that advanced diagnostic capability. They've now upgraded the remote support, like all the guys are doing. I see the Tom Wright guys are doing it, and BV guys are doing it, which is a bonus. The ASI system, I think, is fantastic. The old ones used the magnetic and proxy switches, which were horrible. And the new ASI systems are all built in with the PLCs. That's actually really nice. New feeder designs. Oh, okay. So I'll just flick to the last slide. And you can have a look at the overall layout of the plant, which is a big plant for Zimbabwe. And it shows guys are still investing. And we were talking about the rarity of diamonds and how difficult it is to find deposits. Our clients took a big risk here and a big investment on a fantastic mine so far that's been running for two decades and still producing. But you can see the dual front ends, rotary barrels. There's the secondary log washers, secondary cone crushers. All of these concrete blocks here, all the stockpiles, plus 10 off to the 3 XRTs, the 3 conveyor belts. And your minus 10 is off to the 3 DMSs, our final recovery in this area here. And this was, again, February. We've now put gravel on all the earthworks and tidied it up a bit, but it looks nice. So that's a basic footprint of a sort of a modern hard rock kimberlite plant. I think the concept of the bulk X-ray XRT just becoming a set in stone on our flow sheets here. Whatever you choose, whether you choose Bureveshniks or Tomras or any of the other brands out there. But that's been a major game changer. We ran an operation in Lesotho for 4 years now with 2 XRTs. I'll give you some good data. The gentleman before me was giving us some nice operating cost data. But we're sort of sitting at about 3 Rand 50 per ton, 3 Rand 50 a ton with power per machine, which is fantastic, you know. So we ran 2 machines up there for a couple of years, sitting with power at 7 Rand 50 a ton for the 2 machines. That's really really good data. I mean, there is a caveat to that, though. We had a very high level technician on the ground. So you're talking a highly paid guy looking after the machines, like, you know, whether it's bulk X-ray, it still must be like your final recovery. You got to look after the machines. A lot of these machines are shoved out into the mud and into the environment, and they're a complex machine, and you can't do that. So you got to look after the machines. If you look after them and you get predictive maintenance on the J chutes, when to replace them after X many hours, and you just look after it, you have good voltage control, you don't have big power surges, and you're not going through those sensor bars and all those funny things. And a high quality technical team, or one high quality guy or two high quality guys, then you can sit at those numbers. I've seen the numbers scream when you don't look after the machines, and the machines start packing up. So yeah, sitting, as I say, R3.50 a ton, and maybe somebody can write that down. That's good info. All right, so that's my hard rock plant, big layout, recent, being commissioned as we speak. And I'll now move on to our next plant, which is, this was Zimbabwe. And just as this was ending, we were awarded a contract for up in Angola, 30 kilometers from Katoka. I saw the Katoka pit just now. So this is going to be Luashi. Some people pronounce it Luash, L-U-A-X-E, some Luashi. This is a big plant, 1,500 tons an hour run-of-mine feed. It's weathered kimberlite, completely different. So we're sitting at 30 to 70 MPa. And it just, the mill obviously chose itself, autogenous mill. We're quite lucky. We've been involved in a few autogenous mill designs. So we grabbed this opportunity. It was really nice for us. 30 to 70 MPa. I just put some salient points here. We're the first guys, I think, on a kimberlite. Somebody can correct me, with the eccentric roll crusher. Some of the problems being had at Katoka at the moment is hard rock getting into the MMD mineral sizes. And as the pit, obviously they're getting to deeper now, and there's more competent material, but the igneous or the waste rock, there's a lot of waste rock as well, and then it really stuffs up the conventional roll crushers that were so good on soft clayey material. So we've got a dual feed here as well. So if the really soft tufaceous material direct feed straight to the mill, well, we're quite lucky there. We've probably got 150 meters still of that left to go. And then when we get this contamination, either very hard kimberlite or this which is rare, but it's mainly contamination from the waste rock, which some of the material sitting at 200 MPa plus, we can feed it into this eccentric roll, which a supplier, I'll come to it now, I can say that it can handle up to 400 MPa. I don't know, I haven't come across a 400 MPa rock, or maybe I have, but that sounds pretty hard. So yeah, so we've got we can handle the hard feed and a soft feed. I'll come to the risk with that just now. So we designed a 1,500 ton an hour. Just check my time. Yeah, hurry up. Designed a 1,500 ton an hour, the ERC, eccentric roll crusher section. And then downstream, there's phase one, there's 3 milling streams. So very similar to Katoka, there'll be 3 mills. We've just done phase one at 500 tons an hour. We've got a big front end doing 1,500 tons an hour to a stockpile, and phase one for now, autogenous mill. And obviously, again, here comes the XRTs are popping up again. We've got quite a complex canister system to handle the concentrate from the XRTs now, because it's a bit more complicated, because you're getting a direct concentrate from the very, very low yields from the XRTs. Have got to be transferred across to the sort house and mixed with the glove box pickings. So yeah, you'll see a big thing here is once you've done the big front end with the mill, our footprint downstream reduces significantly, because in the initial phase of 70%, 80% of our material goes to slime. So in the previous hard rock plant, you saw big DMSs. Here you've got a much smaller DMS. You've still got 3 XRTs, but you've got a much smaller downstream footprint, which is great. This project, though, because of the big mill and the big front end, 8,000 cubes of civils up in Angola, that's a challenge on its own. yeah, 10 megawatts of installed power. So this is just phase one. So we'll end up probably at about 25 megawatts, 20 to 25 megawatts, I think, for the plant for the 3 phases. John, you asked me to put a map in, but I just pulled this off the internet. So we are in Angola, northeast Angola, 30 kilometers from Katoka, 30-kilometer radius from Katoka. And the kimberlites, I believe, speaking to the client, very, very similar to Katoka, which has helped us with our design. Fortunately, it's always nice to have a reference point. Obviously, differences in the pit, but my colleague talking next, Rainer, will just go through a bit of the basics on the geology. Here we are on site probably 2 months ago. I think the right picture puts the scale of the project into perspective. I mean, on the right, top right is low-grade waste that they've stripped already from the pit. And you can see there's a 140H grader, there's a 980 Liber, and this is the plant site. So we're busy stripping and got 400,000 cubes of laterite required for compaction. Yeah, so it's good fun. It's quite a challenge. We're having a lot of fun. Record rains, as we saw in SADC area this last season. This was just after heavy rains. You can see we haven't put the laterite down, then we redigging and recompacting. So good fun up in these areas. This is the layout, as you can see. The direct feed left out of picture is the 1,500 ton ERC module feeding onto the stockpile over here, and bypasses and direct tufaceous material is 500 tons an hour straight into the autogenous mill. Then after the mill, everything becomes simple. That's the real bonus of a mill. I know, again, don't ask diamond breakage guys. I think, I don't know, the old bankable feasibility showed Luashi at about $90 a carat. They've mined for 3-4 years. They've been putting it through another plant. So they've got good historical data on the plant. Hasn't been a lot of big stones, hasn't been a lot of high quality goods, but 90, I think with the diamond prices now, I might be seeing at 120, 130. I'm not sure, but the mill really works on this for liberation. And that diamond breakage versus liberation, I think will have to be weighed up. But I'm very impressed with it. It's a Tyson Krupp mill. I'll come to that just now. And as you can see, then we've got classification, primary classification, all the -6 in this case, not -10, off up to the top right. That's our DMS stockpile, feeding 100, much smaller DMS, gravity fed DMS. Client says the mine's going to be there 30, 40, 50 years. He doesn't want a cyclone feed pump, and he's right. He's right. You know, we've tried to argue and complain. He said, Derek, once it's in, it's in. It's a gravity fed cyclone, and it's no moving parts on the impeller, and nice steady feed. And all the +6 is classified into 3 fractions, 6 to 12, 6 to 15, I think, 6 to 15, 15 to 30, and then we've got a 30 to 70. So we've got the client's taking a bit of a punt on large diamond recovery, which is becoming quite common. So he's got a 30 to 70 fraction he's gonna give it a whirl. The nice thing about all of these screens here, if that doesn't work long term, you can change your classification between. It's a nice thing about XRT and DMSs and having big classification. You can sort of play with all your different, you can go 4 millimeter to the DMS, 8 or 10, then change your fractions here and build a bit more capacity on this side. All of the coarse XRT tailings, there's classification again, up into surge bins, and then we've got IMS recrushers and pebble crushers. We've got an IMS tertiary crusher, and we've got a pebble crusher. So similar to the big IMS units you saw in the last one. And then refed, everything recirculated back to the mill. So ultimately, anything leaving this plant is -6, 100% -6. And we've got a big final recovery where we are using Bureveshnik machines. The client is familiar with them, and there's spares and there's redundancy in the area, and there's technicians. So yeah, we're a bit worried about those with the situation and the problems that side, but we hope they get delivered. We'll see. Here's our ERC. I just mentioned the dual feed. The hard waste will be fed through this. The hard waste mixed with kimberlite will be fed through this machine. 400 MPa rocks that the supplier claims can handle. Interesting enough, we don't have to, with an autogenous mill, we've got a 300 millimeter closed site setting. So we've got a 1.2 meter top size boulder going in and a 300 millimeter closed site setting, which is great. So the other interesting thing about this is the autogenous mill doesn't need slabby material. So we selected this because of the uniformity of the product. You want a nice rectangular slab or block or cube or rounded particle going into the mill for the milling, for the AG milling. And this machine delivers a better product than, say, a jaw or a gyratory. A gyratory might be a problem. So we're hoping we get a better shape product, which is critical for autogenous milling. You know, autogenous milling can be a dark art. I mean, everyone will come with theories, but we run a few. Sure, it's got its challenges. So here's the eccentric roll crusher. I just wanted to show you guys. Like there are a few of them in the world. One was in Indonesia, I believe, on a big tin or copper project. One was in Australia. One was somewhere in Europe, and one is going to Russia now. I'm not quite sure where. But funny enough, the 3 projects that I know of were shut down. I don't know why, war and care and maintenance. So currently there's none running in the world. So it is a project risk. We've tried to de-risk this as much as possible. One of the things worrying us is obviously a tufaceous mix with the hard rock. You can see where my little cursor is. There is a bit of a grizzly that scalps or fines ahead. And it's quite interesting. This crusher runs clockwise as you start it, and then as it gets lowered, it's counterclockwise. So it increases the time in the crushing chamber and the contact of the roll with the rocks. So it really increases the efficiency of the machine. But also the tines, then what it does is it cleans the tines of the fines, and all the fines run backwards here. So great unit, concave jaw, very interesting. So you've got a concave fixed jaw and this rotating roll, which has grooves. 146 ton unit. The unit we bought alone is 146. So our front end for this plant is massive. The mill is close to 200 tons. This unit is 146 tons. Challenge with logistics up to northeastern Angola. The mill we've divided into 4 pieces, and yeah, it's going to be interesting. Keep an eye on the space. Let's see. Okay, autogenous mill, there she is. We've put a big overhead crane, ThyssenKrupp. We were lucky to buy this on auction. I think this was the old Petra mill that was going to Williamson. We refurbished it in our big, in the old Doorbell Engineering Works. Only guys that can work on a 7.5 meter diameter shell, unfortunately, in Africa. Can you believe that, with our fabrication facilities? So it was about to close. Some guys have bought it. I think it's called K9 or something, or K9 Fabrication Works, and I think they're related to the NCP milling guys. They've bought it, thank goodness, for our industry, and we were able to refurbish and re-roll and take all the flat spots out of the shell. And we've put a new girth gear on. We haven't gone for the complex ThyssenKrupp. They've got I've forgotten the name, Corvex or something gearbox with a meshing between the. We've gone for a more conventional old style gearbox so that we can fix it in South Africa, and we don't have to get technicians from Germany and that, so we can fix it ourselves. So we put a new gearbox on. So we basically, when we bought the old mill, it was just a shell we wanted and the lead pipe, and everything else we're doing a challenge on this as well. Rainer will come to that. Mill discharge crates, getting the right mill discharge crate and design, getting your product right onto classification. Yeah, there you can see the mill discharge end. That was February. You can see a man, bottom right here, just shows the size of the mill. Quite a beast. 2.5 megawatts installed. Yeah, so it's a big beast. That's more than the Kotoka mills, and it's more because of the problems they've had with harder rock at Kotoka. So we've upgraded, and I think it's a good thing. Downstream, I mentioned earlier, just quickly, we've been through this, but you've got your 3 XRT stockpiles, your GravMax, not GravMax, your gravity-fed DMS, and your final recovery. And there's a big security and access area over here. Okay. I mentioned DMS only 120 tons an hour. The big thing with this project, the guys will come to it after me, but slimes handling is another beast because of this tefacious and the smegmites and the talc and all the other clays. It's a different animal. So the mill's really great, simplifies your concentration step, but our slimes is a challenge, and Yashin and Raina will bring that up now. Our XRTs, you'll see on this whole project, we've built everything. Even if I go back here, look at this. We've built all the, we're going to have 9 XRTs in the future, but we've built all the civils, even the DMSs. We've built the civils for the next phase, for the next 500-ton phase and the next 500-ton phase. So we're taking that 8,000 cubes of civil, we're taking the hit now. So we're going to be going into phase 2 and 3. And you can see here's the XRTs. There's only 1 XRT getting installed now, but you've got space for another 2 either side, and another 2 and another 2. So 3 DMSs, and the recovery is expandable and modular. You can clip on all the extra X-ray machines. So the entire plant is like that, including the milling section. So we've bitten the bullet, and we're doing the civils for everything. Here you can see the XRT building. It's a monster XRT building. There's a man, and the first 3 TOMRAs are going in. They're already on site. They've already been shipped to site. And yeah, you'll see much lower than the TOMRA system. We've done away with the used feeders ahead of it, and we're using the Vibramec prep screen directly ahead of the machine to feed the TOMRA, which saves tremendous height in the building. It's got very simple. That was a huge technical challenge, and we've worked on that hard. We learned on Maroa what to do there. It's about motor sizes, isolators, and all sorts of funny things, because you want the exact distribution, same as the used feeder, onto the belt that's running at what, 2.4 meters per second or 2.2 meters a second. Got to get that distribution right. But as you can see, we don't have a vibrating feeder. Most of you guys will know it's screen, then feeder, then this, we've gone direct. And that is working for us. That's really nice. And then you can see we're doing all the steel, and the next ones can just slot in with all the phases. All the light gray there will just slot in. There's all your compressors and ancillaries. Okay, so there's the XRTs. Burevestniks, this was a picture taken 2 weeks ago, the new BV machines. We have got 10 of them, I think 8 or 10 of them, hopefully on the water in the next week. And we'll see how that turns out. Interesting, we learned from Katoka here, we didn't use the supplier designated machines on, we used still Burevestnik machines, but we used different model numbers that have been very successful at Katoka. So we learned a little bit from Katoka, which is good. So our final X-rays to all BVs, primary and secondary. All the XRT and X-ray concentrates. I just thought I'd put this in, the picture of myself there, John, looking happy.
About 5 minutes, Derek. You're going.
But yeah, I'm nearly done. Yeah. All right. Okay. This is final slide. So just some basics again. We all design glove boxes. This is Fusitron in Cape Town. They've been around a long time. And I really see if you're sorting for 12 hours a day, your seating position, your lighting, your gloves, having space to move in your gloves, and access in the glove box to all the critical equipment. Really great glove box, expensive, of course. It's all done out of stainless. And then we've taken their standard canister system, because here they're taking glove box pickings from the bottom here and then up past my left shoulder into their final sort house with a really nice, simple canister system. And we've got another system which is not here with all the XRT concentrate that also gets shipped, because a much coarser product up to 70 millimeters. So we've custom designed our own canister system for our building for all the XRT conks. So glove box conks into our final sort and our XRT conks, which you can't see here from the right, and straight into the final sorting area. This is another project here that we were involved with. Now, this is not, but it'll look similar to this. Yeah, that's a quick rundown. I know I'm running out of time. I could talk for hours. So, John, yeah, I'm done.
Fantastic, Derek. Wonderful to see that these projects are going on to the north of us. You know, we need a few more in South Africa, and very impressive, Derek, your attention to detail, which I guess is what you started with.
So Derek, the Bill McKechnie here, I'm just wondering, is it, so the XRTs are for the +6 product you said, is it? And the Budavestniks for the finer material?
Yes,
Or
yeah.
is it-
So we're,
Yeah.
correct. So we've the XRTs are for +6 on the last slide.
Yeah.
And then the Budavestnik X-rays are for the DMS concentrate, which is -6.
And are you in charge of the slimes management and all that sort of stuff as well? Now, I guess the tailings will be quite a challenge there.
Yes, we are. It's a massive challenge. I mean, this next slide, the guys are going to go through some of the. We're busy with the guys will just do the plant stuff, but we've just got all the slimes. Rano next up spent time on site gaining information for the slimes guys. Yeah, we're only starting the slimes dam design now. It's a hell of a challenge. Eh? It is. We've been looking at co-disposal, obviously. We're really battling to get the material to with this viscosity to so we've got to pump it. So that phase 1, we've got to pump to a dam minus. Yeah, we've got to pump all the slime to a dam, and the 1 to 6 is just going out conventionally on a belt, which increases the OPEX significantly. But we have, out of this last test work, we have got some interesting information that we could possibly centrifuge on phase 2. We could use a centrifuge and get a 20% moisture, which can go into a belt, a 20% cake. But filter pressing and paste thickening with this tophaceous stuff, yeah, it's a challenge. Eh? So,
but hopefully with depth things will improve.
Yes, we are hoping that. Correct, we are. So we really are on worst case scenario, and funny enough, all the worst case scenario stuff that Yashin and the next he predicted worst case and did his calcs. Thank goodness, because the test work took so long. But it came out exactly as the worst case, unfortunately. But
Thank you.
Right.
You know, Derek, there's a question in the chat box just about rehabilitation, and I guess, you know, it's something that's in everyone's minds today. I mean, we talked about it yesterday. I mean, there was it last year, a big spill at Katoka into the adjacent river, but so that's obviously focusing your minds. And you know, as these big projects get out there, rehabilitation and compliance become more and more important as well.
Yeah, absolutely. I mean, the way it was done in the past in Angola was shocking. So the mandate from our client was to just jack the whole Angolan standard up, which is what we've done. We've taken. I mean, we've taken 8 months now on this. We haven't even got to the final design, but because of the previous problems, we're really careful. We're between 2 major river systems. The one river is really beautiful, so we've gone out of our way to select the right area and deposit in the correct latest methods and world-class methods. The design's still coming out. There's still some work to do, but yeah, it is our whole focus has actually been we almost reverse engineered this from the slimes dam back to the plant. But we're under a lot of scrutiny, and it's been driven by the Angolan government, which is very good. They've been driving that in the environmental side, and nice to see.
So just to introduce Rano Peters. Rano's a senior minerals processing engineer with over 10 years experience in the design and commissioning of minerals processing plants. And then his colleague, who's also going to assist and talk a bit later, is Yashin Ramadan. Yashin is a senior minerals processing engineer with close to 20 years experience in the design, commissioning, operation, maintenance, and so on of materials handling and physical separation plants. So we look forward to this next set of talks, and over to you, Rano.
Okay, thanks, John. Yeah, hi everybody. This presentation of Yashin and myself is just about a project that we're busy with at Consulmet. It's one of the projects Derek has been talking about, the Luashe project, and we're basically just going to talk about kimberlite slimes. So how we're generating it and how we're planning to get rid of it. So just a quick outline of a presentation. I'll basically be setting the stage about why we're interested in kimberlite slimes before handing over to Yashin. We'll take you through the technical aspects of slimes disposal. So just a quick introduction. You know, I'm sure Derek already just mentioned this, but Consulmate, who we are and what we do, the project purpose. I'll take you through Luashe, what we're designing and building the minerals processing plant to do. Just some more background about this project. The common pitfalls, you know, where things often go wrong or where we found things going wrong in our experience. And then the objective of the test work, what we tried to achieve, the methodology, how we try to achieve it, and then Yashin will take you through the outcomes. So just a quick introduction again. So we're Consulmate, and we're a specialist engineering group focused on fast-track design and the construction of minerals processing plants. We execute projects worldwide, and here just a couple of pictures of some of our projects. So this is, you know, it just goes to I'm trying to show the range of clients we have and the range of plants we do. We do greenfields, brownfields. Here on the right, we've got another autogenous milling plant in Botswana. In the middle is our bread and butter, our modular DMS. And here on the left is a drill chip sampling plant we did for Stella or Shore Gold. So, I mean, I don't know if you can see my cursor, but here we've got the kimberlite samples. I think you can see the drill rig there. And here's the entire sampling plant that that fitted into a container. And this was done for Rio, Canada. So basically, yeah, we do production-ready minerals processing solutions. So this specific project we're going to be talking about is the Projecto Luash, and this is a greenfield diamond mining plant in the Lunda Sul province of Angola. So it's open cast mining and truck fed. So you can't see it here, but we've got a common front end and then a modular processing plant with which is upgradable in 500 ton per hour increments. So it's a common 1,500 ton per hour front end, and then we've got the 500 ton per hour streams. Initially 500 and later in subsequent phases, we'll be able to upgrade and duplicate those streams. So this project has a tight schedule, and the project lead time was a significant factor for the project award. And as mentioned previously by Derek, the client operates a sister mine about 30 kilometers away. And it helped us a lot. It allowed us to do benchmarking and was extremely useful for equipment sizing and mass balancing. So just a little block flow of what we just saw. So we've got ore reception and primary crushing, common 1,500 tons an hour, and then comminution with an autogenous grinding mill. So from here, everything is a 500 ton per hour stream to be duplicated later. We've got milling for liberation and then screening, -70, +25, -25, +12, -12, +6, all going to XRTs for coarse diamond recovery. And then the -6 +1 going to the DMS that Derek showed. Concentrate goes to final recovery and hand sorting. -6 millimeters goes to tailings disposal, and the coarse stuff gets crushed again to have another go at concentration. -1 goes to the water recovery, which Yashin will take us through a bit later. Just some project background. Here's a photo of the mining pit being developed at Luashe. Here we can see some of the pyroclast kimberlites or the gray kimberlites, and here's some of the red ones, the tephacitic, and here's some of the VSR stuff. If we look next door, at the next slide, here's an aerial view of the pit as it's being developed. Here in the top left corner, we can see block C1, which is the first mining block that they're going to mine. So for Luash, the top 10 meters is Kalahari Sands. Then subsequently, we've got 40 meters of Kalonda sediment, and then we start encountering the three ore bodies, which is the tephacitic kimberlite or the red kimberlite, the pyroclastic kimberlite or the gray ones, and the VSR or the volcanic sedimentary rock. So the tuffositic is soft, sticky, and it has a clay-like texture, and is very susceptible to softening when wet. The volcanic sedimentary rock lies on the edges of the chimney contour, and also it's found between the two other kimberlites. And lastly, we've got the pyroclastic kimberlite, which forms the bulk of the ore body. It's harder than the tuffositic kimberlite, but it's still clay rich at the shallow depths, and it is fairly soft, but with hardness increasing with depth, and it has a strong correlation, the hardness, with ore density. So just the common pitfalls, I mean, Derek did take us through this, but basically what we've identified is that often where things go wrong is comminution, and getting the right discharge, or getting the discharge grade right, and getting the split, the subsequent split after comminution into the rest of a concentration plant right, is often fairly difficult and fairly challenging. And then also water recovery, getting thickness sizing right. And of course, I mean, we've also seen a couple of catastrophic failures of slimes, dams and stuff in the recent past. So it's definitely something that we've highlighted that we'd want to get right. So then, to try and get this right, our objective was to try and characterize the ore as much as possible. We split it into two: comminution and the slimes test work. And for the comminution, we identified the T10, the A times B, and the bond work index. So the T10 is a breakage index. It indicates the percentage passing the 1/10 of the initial mean particle size. AB is an index or indicator of ore impact hardness, and it's also known as an impact breakage parameter. And these two are commonly determined by drop weight testing. We used something similar, a hardness impact tester, and I'll show that in the subsequent slides. And then, of course, we have the bond work index, which is the energy requirement for size reduction. And then on the slime side, we looked at flocculation, settling flux, and slime rheology. So in order to characterize the ore, we sent a containerized lab, to determine all these characteristics. It was fully kitted out. As you can see, we had a jaw crusher for size reduction of these drill core samples. We have a hardness impact tester here in the top, which is a weight, a predetermined weight at a certain height. Put your ore particle in there, and it drops, and the energy that it absorbs is known. And then, of course, with the sieves here, that you determine how the particle broke up with this drop here. And then we also had a mill to do some comminution for the slimes test work. So with the information we got from the hardness impact testing, we were planning to do PSDs, use that PSDs to generate a slime sample, and send that slime sample away for further characterization. Okay, so this just goes through the drill campaign. We were planning to do 16 drill cores of the C1 mine block up to 200 meters deep, and then have the geologist identify the different ore types at depth, and then using the instruments and the equipment I showed on the previous slide, we wanted to, and thus doing, generate and characterize and get a picture of what the ore body would look like for this mining block at the different depths. So the test campaign would have used a HIT, or a hardness impact tester, which is very similar to drop weight testing, but it's not patented or linked to JK. We would do PSD simulations, which we require for sizing of the subsequent concentration circuits, as well as the slime settling test work, and then to send 200 kilograms of each for further sedimentation test work. So the outcomes, unfortunately, comminution, when we were doing the test work, we didn't have the right type of sample. We couldn't get enough of the right type of sample. We only got shallow samples, or enough sample to be statistically relevant. Of the test work that we did conduct, the ore was all very soft. We got A times B of 170 to 400. And for the crushing index, usually 120 to 300 is very soft. Bondwork index, the grindability, we got 5 to 10. And of course, that's also soft or very soft. So what we had to do is, of course, as Derek mentioned, we had to rely on the historical data from the sister mine, as well as some of the bulk test work that was done previously to make our assumptions and do our mass balancing. And this will be supplemented by further test work. The guys on site, the client is busy generating more sample for us. So what we did is we prepared for worst case settling or very fine liberation to do our slime sizing. And this is where Yashin will take us further.
Good afternoon, good day, good morning, folks, to those of you not in South Africa, those of you in South Africa. I hope you're managing the cold and the load shedding. We're struggling a bit on our side, but yeah. So, sedimentation and slimes treatment. I'm going to chat to you a bit about this part of the project. So the way we do it at Consulmet is we split up our plants into various sections, and we have discipline engineers. And in terms of the process engineering side, Reno was on the front end for comminution, and I was on the tail end for water recovery and sedimentation. So, challenges. What are the challenges that we faced in terms of this project for, well, the Luashi project in Angola? Firstly, it's in Angola, some 3,500 kilometers away from Johannesburg here. Water recovery by means of thickening is not common at all in the region, if not in existence at all. That tells us that we have limited operational data to gather from a design perspective and a sizing perspective. Slimes handling is a big risk, especially since the latest failure or the most recent failure at the Katoka mine, where the slimes dam wall breached and ran off into one of the major rivers which fed into the DRC. Service and capabilities. What is available in the region when you're constructing such a large project with large equipment in terms of steel handling, craneage, etc.? The project is ongoing whilst we're busy looking at the operational data and the test work data. So there's a massive time constraint in terms of what's going on. Our approach was to look at the historical data that we have in terms of the Consulmet plants built to date. What have we done and how have we done it thus far? From this, we could put together a set of a data set where we could do a comparative analysis and form the base case design, as in slimes content, settling rates, yield stress by means of thickening or underflow density, etc. What could we achieve? We then took this data set or these data sets and approached various suppliers within the market to understand the pitfalls and drawbacks and limitations on the various technologies out there, be it high rate thickeners, paste thickening, filtration, centrifuging, etc. Combining the data sets and analysis thereof with supplier interaction, we formed the roadmap for the design, the equipment specification for the thickener and flocculant plant. And I'll explain more on this a little later on in the presentation. Whilst this was happening, we formulated a rigorous test work program, which we went about putting into place to actually get the slimes test work carried out so that we could validate our design. The design path. The design path addressed some of the common issues addressed with most kimberlite treatment plants in terms of thickening and water recovery, one of which being slimes handling, which is the sub 45 micron, the thickening and handling thereof. So this includes the smectite clays and the talcs. Where do you put this? How much do you have? How do you put it into the tailings dam? At what solids concentration do you put it into the tailings dam, etc.? The grit or the degritting process. How do you go about selecting the degrit plant? What do you cut what do you cut at? 300 micron, 1 millimeter, half a millimeter, and how do you manage this? The process water quality, of quite high importance, the process water quality, because this affects the operation of the DMS, the upfront comminution circuit, etc. And I think if the most challenging and most important, the design and constructability in our case, how does one go about putting up a large diameter thickener, say, let's say, for example, 50 meters in diameter in an absolutely remote location with a semi-skilled workforce and limited site services as in craneage, rigging, etc. These were the design challenges. So I'm going to go through each one of them slide by slide and give you a little more insight and background as to how we overcame these. Slimes handling. So we took a systematic approach to the fines capture or the slimes handling. And in this instance, we consider slimes minus 100% minus 45 micron or 50% passing 20 micron. So indeed, very fine for flocculation and coagulation. We've catered for multiple phased addition of flocculant points within the thickener. So we could get as much of the flocculant into the thickener feed. We've also added a few coagulation points for future use if needed, and designed an internal dilution system with the sub-suppliers, a competent internal dilution system, which manipulates the free settling rate of the feed solids entering the thickener. So in essence, if we're adding 10 cubes an hour, 10 cubic meters per hour into a thickener at 20% solids, we use the clear supernatant within the thickener to drop that down to 5% solids by mass, which substantially increases the overflow clarity and settling rate. In essence, counteracting the effect of hindered settling. The degrit systems. So in this instance, our degrit circuit works from 300 microns and above. So we cut at 300 microns. So the minus 300 microns reports to the thickener. The importance of a degrit system is firstly to reduce the thickener size because we send less solids to the thickener. Secondly, the degrit circuit removes the plus 300 material and you are then able to transport this in a semi-dry format to be used for impoundment creation, slope creation, dam creation, etc., without passing it through the thickener. Thirdly, you don't need to pump this through the thickener, which reduces the wear rates and pumping capacities, etc. Now, what we have done here is we've designed a thickener with a dual flow slope. And what that means is for the outer 2/3 of the diameter or radius, you have a flow slope of 7.5 degrees. And in the inner third of the diameter has a flow slope of 15 degrees. That gives us massive flexibility and increased capability in the essence that we need to increase the grit cut point to, say, for example, 1 millimeter or 500 micron, or a very simple fact, if we lose screen panels along the way. And that happens in an operational plant. One would lose a degrit screen panel and start to pass grit into the thickener. Now, when this happens, you start to increase the mud bed density and decrease the solids bed flowability. We have counteracted this by increasing the drive torque and having a dual flow slope. Process water clarity. What have we done here? As explained, we have multiple flocculant addition points to take care of the -45 slimes fraction. We are also going to be use benign cation salts, excluding chlorides, to increase the process water clarity. What this basically does is it changes the water chemistry so that the clay particles do not swell. Slimes or clay particles, in essence, present themselves as either naturally dispersed or naturally colloidal. Naturally dispersed particles will not settle under gravity. Naturally colloidal will come together and settle under gravity. So by adding the benign cation salts, we change the particle chemistry to suit what we need for flocculation and coagulation. Hence, we get a much higher increased settling rate and water clarity. We have implemented the system on three operational plants thus far, and have reaped the rewards of this. The thickener construction. As I said, this is perhaps the most important point here. How to safely and economically transport a 50-meter diameter mild steel thickener into the heart of Angola. How to erect this unit. This is how we went about it. We used a bolted construction platework assembly, which means the platework is simply bolted via lap joints to form the structure that we need. Flat pack construction means box truss sections are broken apart and laid on top of each other, and they're just simply assembled on site. The tank design is quite a novel hybrid tank design, whereby we will use competent backfill material to create an above ground impoundment. Within this above ground impoundment, there will be an access tunnel through which the underflow piping and service access can be will be sorted out. The above ground impoundment will then have a concrete floor structure which has a cast in ring beam, and to this we will mount or bolt the bolted construction side plates. And from the series of pictures at the bottom of the slide, you will see what I'm referring to. This saves us approximately 300 tons of mild steel for fabrication, transport, and site erection. So in essence, we don't need a 50-meter diameter mild steel tank, which is supported by steel columns and concrete plinths some 10 meters in the air. The next slide shows you exactly what we're talking about. You have the above ground impoundment, the mild steel sidewall structure up top, and the thickener underflow tunnel at the bottom, capacity-wise. Thickener sizing and selection is driven primarily by the solid settling flux. If it's a thickener, and it's driven by rise rates if it's a clarifier. In this instance, we drew on our combination of database information and industry experience to choose the design flux. And Derek had mentioned earlier on that we went for a quite conservative approach on the design flux. And that came in quite handy because we have sufficient capacity, and the test work has actually shown that we need the design flux that we had chosen. This then sets the tone for the diameter required. We then chose a higher than normal sidewall for the thickener. Typically, for a 50-meter diameter, one would choose a 3-meter high sidewall. In this instance, we chose a sidewall of 3.8 meters high because we understood the dynamics of kimberlite thickening. Overflow clarity is an issue, even though we're adding benign cation salts. So a higher volume would allow a larger retention time for the clear water clarification. We then also added an additional factor whereby we could increase the mud depth height. And the mud depth height simply means a higher underflow solids concentration. Well, one would say, well, if you've got a higher underflow solids concentration, you would get an increase in underflow yield stress. Yes, we catered for this by increasing the rake drive torque to counteract any potential yield stress which might be developed during the thickening process. and grit contamination. We went one step further. We omitted the rake lift system. Larger thickeners, in terms of thickness above 40 to 45 meters, do not benefit from rake lift systems because they become quite cumbersome and do not have substantial torque to lift the rake drive a significant height out of the mud bed. What we've decided to do here is increase the rake drive torque capacity by some 50% so that the rake drive would rather plow out of the bed or through the bed rather than lift out of the bed, the solids bed. Some of the pictures here show you what the end product looks like. The picture to the far left shows a column type drive unit with multiple pods and a large central ring gear capable of extremely high duty rated torque factors. The center picture shows the feed well which was employed, which has significant internal dilution and a dual type feed well system, which also allows for very efficient flocculation and coagulation. And the third picture shows the culmination of all the technology which we have put together. The dual force floor slopes, box truss rake sections for low drag, high underflow density situations, the dual feed well with dilution slots, and the center column drive unit, which actually allows you to use a half span bridge instead of a full span bridge. Now, this is a massive saving if one considers that a 50-meter diameter bridge is in excess of 70 odd tons. And this is a single lift on site. So here, we've managed to counteract many of the design challenges or design around the challenges which we had been posed with. Again, two snapshots of what the final assembly looks like after we have implemented most of the design changes or design philosophies which we came up with. And that's the end. Any questions and answers?
Fantastic. Thanks, guys. Just to kick off, I mean, again, I guess the name of the game is innovation and costs. Obviously, without maintaining standards, high standards at the same time. That structure you talk about, I mean, could once the material is settled and dry, and I might be missing something here, can you empty it or take away stuff and lay it out on the ground and then reuse that, or what do you do long term, Yashin?
John, are you referring to the thickener?
Yeah, to the thickener.
Itself?
Yeah.
So the thickener is a dynamic unit, and what it basically means is 1 ton in equals 1 ton out. So
Okay.
you input 1 ton at a very low solids concentration. In this case, probably around 9% by mass. However, you withdraw the same tonnage at a much higher solids concentration. In this instance, probably going to be around 35% odd by mass coming out of the thickener. So this is then pumped via the slime system to the slimes dam, and the aim of the game is to pump as high a solids concentration to the slimes dam as possible. One, because you reticulate a lot more water within the system, and you lose a lot less to evaporation. And secondly, and I think of more importance, your slimes dam capacity or footprint becomes much smaller in terms of what you're pumping to it.
Yeah. Okay. And I mean, how stable, you talk about 35%, and excuse my ignorance, I'm not a metallurgist, but how stable would that slimes dam material be? You've obviously still got to contain it and build a wall and so on.
Yeah, so the wall's built using a mix of various particle-sized material and various types of material, obviously to give you stability. And the wall's built at a certain rate of rise and a certain angle, and basically that's called your impoundment wall, and you then start to deposit within the tailings dam facility. And the clever geological guys on the other side of the tailings dam management system design that in terms of what's the rate of rise and what would the water bleed off be, but it's pretty stable provided that you keep the water management to to the design criteria as such, and not let it fill up with too much water, because you start to get breaching of the walls.
Yeah. And just obviously, mindful of the environment again, you talked about using flocculants. Obviously, those are all benign, and the one positive thing obviously about mining kimberlites and the way we do it, we don't use any nasty chemicals.
Yes, exactly. The flocculant, after a while, the long chains would break down, and the flocculant's fully organic, so it's organic polymer, so it would disintegrate over time.
Okay. All right.
Can I just ask, is there a professional design engineer dealing with the tailings dam construction?
Yes, we do have a professional design engineer on board.
Is that
A team of
yours
design
or is it an
engineers.
external consultant?
Yeah, a team of design engineers externally.
Okay. And is one of them taking professional responsibility for the design and all that type of thing?
Yes, exactly. Well, one would have to do that. It's a must.
Yeah. Okay, and then it's quite good to hear that the Angolan government is now taking this seriously, because there's a lot of legacy issues with slimes dams and so on up in that part of Angola, as you probably know.
Yes.
Yeah, Bill, and I mean, unrehabilitated areas in general. I mean, obviously it's a high rainfall area, so I guess a lot of those original what did you call them, diversions, probably rehab, but certainly in my experience there was always some nasty leftovers, and it'd be good to see that sort of stuff is also being attended to these days.
Yeah, I think it's less of an issue with the alluvials, but the other kimberlite operations that were operated for a while and have gone, open and close. They've left, quite a bit that needs to be fixed.
Yep, agreed. Angela's asked in the chat box, could you provide an example of chemicals used as flocculants and what is the cost impact?
Oh, Angelo. So typically one would use I think these would be high-ish molecular weight, long chain polymers. From a rand, $1 per ton perspective, it changes quite a bit. I could get that information for you, and I'm sure you could get my contact details from John if it's not available immediately, and I could give you a $1 or rand per ton cost on that, roughly, in terms of what the supply and dosing costs are on that.
Yeah, fantastic. Thanks, Rainer. That's what we'll do. And I think Tanya mentioned earlier, we'll collect or ask you to send interesting information like this to me or Tanya. We've got our email addresses, and then we'll compile that and put it in a document that we then circulate to all the participants. And another thing we need to find, Derek, is we need an updated geological paper on Marewa. I mean, it's a fascinating kimberlite. I seem to remember there were 3 pipes, and I'm not sure if there's, in the public domain, if there's a more recent article that you're aware of that we could get hold of.
Yeah, I don't know, John. I think, remember that Rio Tinto originally owned the concession, and they sold it, 5 years ago?
Yeah.
So I don't know what the most recent is, but yeah, I'll look for you. I'll see
Okay.
what I
Yeah,
can
we'll dig around too. I'm sure there is some good stuff. I mean, Rio would have done really good work, and they're normally quite diligent.
It's been a really good mine. I think if you look at the $1 per carat they got and the grades, I mean, the grades were fantastic.
Yeah.
They ran a pretty low-cost operation. It's been a great mine over like I say, the last 2 decades. It's done well.
And it's good to see that. I mean, it's a local company. Who's your client, Derek? Not wanting any secrets, but it's a local company, is it? Or
yes, yeah. It's still the old Riazim. So,
okay.
so they literally bought out Riazim lock, stock, and barrel.
Yeah.
So
there's a question in the chat if you'd like to get to that.
Okay. All right.
For our students, Derek, just a 101 on GMS.
Ah,
Fezzi, yeah.
sure, I could go on for the rest of the time on that. No, look, DMS, dense medium separation, is just heavy medium. So you mix the Fezzi with water and you form a heavy slurry.
And Fezzi is iron silica compound.
Yeah. Iron silica compound, and it forms it's iron silica compound with an SG of like 6.8 to nearly 7. It varies a little bit. And you mix it all together with water and you form a slurry of an SG, typically anywhere between 2.4 and 2.7. So it's a heavy medium. So if you can picture a bath.
Diamonds are 3.5.
Yeah, diamonds are 3.53. So if you put this Fezzi and it was agitated correctly in a bath, the diamond would sink, and all the waste, quartzite and all of that at whatever it is, 2.7, quartz.
2.5, whatever.
2.5. That all floats, and all the waste floats. So the key about DMS is now you add it into a cyclone. So you've got centrifugal forces, and that accelerates the density differential. So your momentum of a diamond at 3.53, when it enters a centrifuge or a cyclone, it pushes through the wall, this ferrosilicon wall. A heavier particle finds it easier to get through to the outside of the cyclone, and all the waste vortexes out the middle, and the cyclone, and basically the diamond comes out the spigot of the DMS cyclone. So you've got the density of the slurry, you've got the inlet pressure of the cyclone, and you've got the characteristics of the material and the cyclone dynamics. Yeah, it's actually a very simple. It's gravity. It's a gravity process. It's a physical process. It's not a chemical process. Talking about reagents, Fezzi is inert. It's not doesn't do harm to the environment. And obviously, it's getting expensive nowadays with commodity prices. You've got to recover it as well in your circuit. So you use magnetic separators to recover the ferrosilicon. You drain it, you rinse it, and you recover it. That's a quick crash course. I don't know if I've covered it enough, but I hope it's enough.
Yeah, that's excellent, Derek. I mean, it's also very efficient for recovering diamonds and other heavy minerals, unless you have bad operators, and if you're not careful, then you throw away your diamonds.
Yeah, it's massively efficient. I mean, I think the most yield we're getting is 2% on some of the kimberlites. Typically, we're sitting at 1.1 to 1.3% yield on most of our DMSs. So, 100% going in, only 1% coming out. You're concentrating. And recovery of the diamonds. If you're running your DMS right, you really got to cock it up to lose the diamonds. But remember the fundamentals I brought up in my presentation. You must stick to those fundamentals. I think guys are forgetting those, like I say, medium to ore ratios. Also tonnages, John. The guys are running plants designed for 100 tons an hour, and then the guys all high-fiving each other for feeding 150 tons an hour. But that's great. But the cyclone, or the DMS cyclone, will become a T-piece. Medium to ore ratios and the feed. You've got to stick to the basics. Rather run a plant steadily and properly, and then run it at 50% above design or 100%, and then shut for 4 hours every 4 hours. I think the guys are not running plants at steady state capacity. They're pushing them through the roof. And sorry, what I was meant to bring up in my presentation was efficiency. Guys are not they're looking at throughputs and tonnages, and that's the natural thing with grades dropping and guys having to push more tons through a plant to make it work. But efficiency has gone out the window. Diamond recovery efficiency, De Beers, they were very strict with all of those recovery efficiencies, and the guys are not focusing on right throughout the metallurgical chain, recovery efficiency. I wonder what that costs a year on every plant.
Yeah, Derek, I quite like the stockpiling that you had set up. I mean, being a geologist and having been involved in sampling programs, we always operated with stockpiles and those things. And the bigger a plant gets, the more complicated the processing gets. As you said, if something goes wrong somewhere, then the whole place shuts down, and the stockpiling just gives you flexibility.
Yeah, that's the nature of our business. We've tended to compact our plants so much with technology and try compress them into such limited footprints that that's sort of fallen by the wayside. But if you can do it, yeah, it's highly recommended.
There's another question in the chat box. Apart from tracer tests, is there any other method to assess the cyclone efficiency?
Oh, look, I've had some, the extreme method, John, is old Chris Potgieter. He chucked a handful of real diamonds in the one day while I was standing on the prep screen. But no, look, I think keep your, there's some fancy viscosity meters now. Viscosity is a big factor, viscosity and stability. There's a formula, I mean, Yoshino Reina also answering the flocculant one. If you want to drop them a message, there's a, I always used to, I think it was the overflow density to the feed density must be within 5%. Greater than 5% was a stability, and then the other side was viscosity. So I think viscosity and stability calculations and measures, and there's some fancy viscosity meters out there nowadays. Yeah, I think it was, I think Cision were trialing them on some of the big iron ore DMSs. Yeah, to me that is key, because it's the quality of your medium, and then yeah, just regular tracer tests as you mentioned, and constant monitoring of your density and pressure. Otherwise, aside from real diamonds, you can only chuck your tracers in and get your and do full. A lot of guys just chuck the diamond tracers in and get them out, but you need to do a full tromp curve. You know, because the tromp curves also will show you the material reporting to that middle fraction when your curve starts to go more horizontal and drops off your EPM. So do full tracer tests. Yeah.
You use different sizes of tracers, obviously.
Yeah, obviously the finer the better, but you know, to do a 2 millimeter tracer test on a 200 ton an hour or 400 ton an hour DMS gets a mission. So I normally do them with 4 millimeter, but every 6 months or so, if you can do them with, if your bottom cutoff size obviously is less than 2, try to do it with a bunch of 2s, but do that at least every few months and take the pain of getting them.
I'm sorry, Derek, just to add on to what you're saying, you could also send the floats and the sinks for heavy liquids.
Yes, Raina. Yeah, you're right. Yeah, so you can, that's a nice way to do it as well. So 100%. I don't know if you ever asked that question. Yeah, so you take samples of your floats and sinks and send it for your heavy liquid separation tests. So if you've got a lab, again, a big mine, and you've got a small lab on site, even a small mine, you can do that. Sorry, back to the tracers. I mean, tracers are fluorescent as well. If you do it with the 2 mils, chuck them in and get them out the X-rays if you can.
And Derek, I mean, we're sort of getting to the stage of wrapping up. Just Jim Davidson very kindly gave us a sort of overview yesterday of how, you know, diamond mining and particularly diamond recovery has developed over the years, starting with the old, you know, axle grease. Just in 2 minutes, why have Burevestnik been so successful with their machines? I mean, obviously, you know, the whole X-ray system keeps evolving, but it's very interesting to see, you know, how successful the Burevestniks have been.
Yeah, they're a rugged machine, they're a tough machine. I mean, I think they've got the pulsed X-ray. I'm not an expert on this. I think you've got the two. They've got the pulsed X-ray in their machine. They've got two X-rays, so they're hit it from 2 directions. So the fluorescence, you know, they really fluoresce the diamond. Again, I say rugged machine. If you saw that picture of those new machines in Russia, they're looking really nice. They've obviously learnt. It's a good, robust machine. You can't argue. The first ones in South Africa had the feeder problems with the free fall material into the machine, and some guys were taking that plate out in the feeder, taking it out. Some were putting it in, but I think all those issues are being resolved. They're good machines. They look, flow sort, DebTech, Burevestnik, everyone's got their pros and their cons. They're all good, and all of them have done work over the years to improve their machines to a degree. Even the Tomra XRT now it's on Mark IV model or whatever it is now, with the S chutes or the J chutes feeding the machine, the quicker computing power, the quicker CPU processing power. So at least we're getting a good selection amongst all these machines. They're all improving, and there's good competition, which is good for us. The BV obviously was supported, to answer your question, it was heavily supported by Russia with all the Russian diamond mines. And if you've got a big brother supporting the machine heavily, they can do the development and install these machines on hundreds of these machines. So the amount of machines they produced has also been a benefit to them.
Yeah, I guess much like De Beers. And then just my experience, and it's interesting, you've commented on it as well, Derek. I mean, nowadays with all this equipment, it does need TLC. I mean, you need proper, conditions, clean conditions. You think of how many old plants you looked at in the past where, you almost drowned getting in the door because of the mud and mess. And having, good quality technicians or experienced technicians to keep all this equipment working smoothly.
Yeah, it's one of my bugbears. I really, if you run a machine well at R3.50 a ton, I mean, that's with the expensive technician. Come on, man, why are you arguing around operating cost then at having a 100,000 Rand technician on the machine? If you're arguing that, the mine shouldn't even be running. That's my opinion. Then something's wrong. So yeah, you got to look. It's the same with all the machines. I mean, we've got clients not replacing scrubber liners and putting new scrubbers in. They'll put a 10 million Rand roller mill, replace it, and not replace the liners. Not spend 8 hours replacing the liners. So it's a general operations thing across the board. It really got a housekeeping around the plants. There's a definite correlation to success and recovery of nice diamonds. When you walk into a sort house, John, and it's immaculate and everything's in beautiful nick and clean, and you walk into another operation, and those guys are the guys constantly on the news reporting the recovery of these stones. And the guys that are just running their machines in the mud, and you can't get to the sort house through the water and the machine is a mess. The last time it had maintenance was 8 months ago, and the guy's asking, he can't understand why. He can't understand why he's not recovering. So yeah, the real basics. I mean, you got to do your housekeeping and your plant maintenance and keep everything immaculate.
Derek, a question from me. Do you have any thoughts on how the Ukrainian-Russian situation may or may not affect Burevestnik?
Yeah, we've been very worried. Because we dealt with BV South Africa, so contractually they've obviously assured us that everything is fine. But the proof will be that at the moment we don't have a problem. If you look at South Africa, we are not sanctioned. I mean, to dealing with Russian suppliers. South Africa at the moment, as far as I know, legally is not sanctioned to dealing directly with if you've ordered anything from Russia, if it be a car or a hairdryer. I don't know if that's a problem worldwide for South Africans. And so on a legal perspective, delivered to South Africa, it shouldn't. So the Russians said no, they can keep delivering to South Africa. And South Africa hasn't implemented sanctions against Russia. We haven't, as far as I know. And so there's no reason why we can't trade.
Maybe a philosophical query or comment from myself, particularly with small or marginal projects. Do you have protocols in place to avoid undercapitalization and overcapitalization in plant construction and operations? Or is it kind of done on a case-by-case basis?
Yeah, we don't have a protocol, but I think as in our business, we should be a lot firmer. There's some things you just can't do. I mean, guys come, a lot of times, unfortunately, in our business, you try and make the client happy and the budget gets smaller and smaller and smaller. And then you're still trying to make the guy happy when you've lost the plot. Everyone's lost the plot a long time ago. So that's on the undercapitalization side. So I think it's up to the professionals to be firmer. I mean, I stood up many years ago at one of our mineral processing events and said, guys, you've got to stand up and say, come on, you know, you've got to be, as a professional process engineer, you've got to draw a line in the sand somewhere. And it's difficult, you know, it's you're always trying to keep the client happy, and I can't really, I think you've got to manage expectations, and South Africans by nature, unfortunately, are quite polite. We're always trying to make everyone happy. Hey, John, we're trying to, you get a guy that's a client sometimes bullies you, and you're trying to make the guy happy, but you've got to draw a line in the sand somewhere. And I think as professional process engineers, it's up to you say, no, that's impossible. No, you can't do that. On overcapitalization, yeah, it's a lot of marginal deposits out there. Your geology must, and sorry, John, this comes back to the geology must give the, I mean, we've had some world-class projects where the guys are trying to undercapitalize it to the nth degree, and you can't understand it because you look at the IRR and it's like 300%, and you say to the guy, but your business model is saying what you can spend here. Yeah, you can't go silly, but you don't have to cut your neck here at every corner. So that's a difficult one. I think it should come from the geology of the deposit. I mean, if you look at the two projects I just presented, they're not billion-dollar plants. They're not even, one of them's a R1 billion plus, $80–90 million. The other one is not even that. But they're still world class, and they're quality, and they're fit for purpose. And we have concentrated on efficiency. But if you look at the business models, our capital suited the capital spend suited the geological model. And I think that's very important. And the time, time to get it in. So it was best practice under the circumstances. I've started on your smaller clients now. I've started saying, well, what have you got? You know, instead of us running around doing 40 different estimates from the cheapest to the most expensive, that just wastes everybody's time. A lot of the times to the mid-tier miners, I'll say, well, how much money have you got to spend on the plant? And then I started, well, I can do that, or I can't do that. I think that's all. I can do this, but these are going to be the pitfalls if you do it for this budget. So it's a difficult question.
Yeah, Derek, it's a good question though, and I think one of the problems, of course, is we've got too many accountants and even lawyers, for that matter, running big companies. And you know, it's a personal gripe of mine. I think we as geologists have undersold ourselves, or you know, we've let other professions take over businesses we should be running. And then it's something you've seen, and we can talk about a lot of examples where you've seen people, managers, engineers, and that you know, move from big companies to junior companies. Liquibong, which you know was a classic example, sadly, and that's probably why it's never worked. You know, and the money that those people who still have this big company sort of approach, and you overcapitalize everything, and you try and build in every possible, you know, option to prevent failure and so on, it just kills the project. So I think making sure, like you doing, that people understand their project, and you get the right geology, and you do it properly, you know, that's the way it's got to work. I think a lot of little projects in this country have been killed, and not only this country, but elsewhere in the world, have been killed because they grossly, you know, overcapitalized by the wrong management. Yeah. Anyway,
you've got to read the situation, John. You've got to read each project, and it's really difficult on the marginal mines, like you say, on the marginal deposits. What does it always come down to, John? Dollars per ton in the ground. I saw the slide, the presenter before me. I mean, he nailed it with that Chuaneng, dollars per ton revenue. Jeez, it's what it comes down to. So you as the owner or the investor, do that number. I mean, if you're getting $10 per ton in the ground, how are we going to build a plant that can operate and pay back the capex at $10 a ton revenue? You can't. So there's a lot of those things you can wipe off the table right now. But a real small guy might be able to go. Maybe there's a big diamond there. It's such a varied subject, John, but it's particularly difficult on marginal operations.